Recording. All right, welcome everybody. Tonight is the 2nd of February in Dallas, or Wednesday the 3rd in other parts of the world. So this is our regular Builders Night out online from Dallas Person Robotics Group. I'd like to welcome everybody. My name is Carl Ott. I'm the current president of the club. And what we do is just go around the table and folks talk about projects they're working on and raise questions. We got a lot of varied and interesting experience online, and we love to have Stump the Club challenges. So what we'd like to do tonight is start off with Iron Rain, a storied robotics high school team from Dallas, led by Kareem, who's always smiling at his intro. And we have a couple of his students online. So Kareem, if you'd like to take it away, go ahead, and then we'll move around the table.
All right. Hold on a second. Let me, wow, it doesn't show properly. Let's see. I think it's this one. Yeah, that looks good. So this is just going to be a quick update of what's happened since we presented last week. And Bonavia will kick it off.
Okay, so hi, we're Team 6832 Iron Rain from the School of Science and Engineering, and you guys already know that. So next slide. So starting off with the week was our presentation to you guys. We presented our launcher system to you. You got to see the very first launch of it. The assembly happened right as the presentation was ongoing, and we presented to you the first version of our equation where we modeled what we thought was the accurate trajectory for the launcher system. Since then, we've made changes to both this equation, to our launcher system, as well as the actual code for it, which we'll discuss throughout this presentation. So first of all, the day after, Wednesday, we start off by planning for the new season. Here's like the list of qualifiers that we have coming up. As you can see, they're pretty close by. We've got about 18 days before the latest one. So we thought about what order we'd like to go in, about when it'd be nice to present. And we know that part of the challenge is making sure that our robot is up and running, has everything that it needs to go before we're ready for these challenges. So we wanted to get feedback from you guys about what we've done so far to check ourselves whether or not we're ready for like our upcoming competitions. And Mahesh will continue it.
Right. So on Thursday, we started revising. Sorry, not revising, but well, yeah, we started revising our previous ballistics calculations, which had quite a couple of errors in them, and so we decided to sanity check our calculations by putting them all into a spreadsheet, laying them out, and plugging in all the values and seeing if they would actually form the trajectory that we wanted them to. And so we built a Desmos calculator we started building a Desmos calculator to actually graph out a parabola of the disk trajectory, and so you can see that on the bottom left. And we started building a Java solver class to actually, transfer the math into code. And on Thursday,
and the quote of the day.
Oh, sorry.
Oh no, go ahead. I was just gonna make a joke about the quote.
Right. So continuing on. Jose also added an additional elbow mount for the support of the launcher on the right side of the turret, just because it was kind of lopsided in terms of its center of mass. And on Friday, we continued discussing modeling the physics of the trajectory and how we would actually control the robot to meet the requirements that we would need in order to launch the disk correctly. And so we revised the Desmos calculator again, and so you can see that where the parabola passes both through the origin and the point that we want it to. And I think there'll be a link for that at the end of the presentation. But yeah.
First try.
Sure was.
Look like 50 of them. Hey,
Did you get the audio from that video?
Yes.
Did people hear that?
Did we hear it? Yeah.
Okay, cool.
Yeah.
So that was the first shot from the actually mounted on the robot.
So on Saturday, Justin and Trey started printing the rev shaft encoder parts for to mount onto the robot. But they also began full speed testing of the flight envelope of the rings. So ever since the assembly of the shooter and since that launch that Mr. Brownie showed to you guys in the previous video, the launcher slowly needed more work so we could test if it's able to launch rings consistently. And we wanted to check what the approximate height it could get to was. So Justin and Trey started testing like it right into the envelope of the post. They also removed the bungee assist in the elbow. So we're actually reusing our robot chassis from last year. And one of the parts that we kept on it was a bungee assist, which basically helped support the elbow up. But for this year's challenge, we don't really need that because we don't need the robot elbow to extend a lot as we did for last year's challenge. So they ended up removing the bungee assist. And another reason they had to remove it was because it changed the launch angle a lot. And also, they dusted a 4 to 8 foot sheet of insulation as a target to locate the rain hits. So another thing about changing the variability of the launch angle. So in our last meeting, we gave to you guys a series of equations. Those equations have still like relatively stayed the same, but one thing that we noted since then is that the initial height of the robot was 0.41 meters, but we found out that as the angle that the robot's launching at changes, this initial height changes also. But we need the initial height to be able to calculate other variables like time as well as initial vertical velocity. So the fact that the initial height changes because of theta is a little bit of an issue, but we plan to correct that by modeling a function for it later, as well as trying to adjust any other variables that could lead to like sources of error within the angle of launch.
Navia, just a question. I'm not clear. Why does the height of the robot change?
So as the elbow raises and lowers itself, the height that the robot's shooting at ends up changing because the elbow is at a different position.
Ah.
Yeah, so when the elbow is like a little bit higher, the height changes. So that was an issue because it affects all of our calculations, and our equation relies on the initial height being somewhat consistent. So we need to model another equation to determine how much the initial height changes due to the angle of launch.
They should probably have a graphic to show that better. The hinge for the launcher elevation is on the back of the launcher. So the front of it raises quite a bit depending on how many angle, what your angle of elevation is. So it's a feedback loop, and fortunately it's a converging function. So they can iterate to solve it if they want, but they haven't quite got there yet.
But it sounds like had you done this again from scratch, you might have put the hinge on the front, and that way the trajectory would always come out of the same place on the robot, right?
Sure. Yeah, that would be easier from a math point of view. Not necessarily easier from a build point of view.
Understood. Thanks.
I have a question. As the arm moves, though, can't you just know what angle it's at and then use that as a variable into the code to assume the height?
Right, yeah, of course. I mean, it's possible. We just haven't accounted for it as of now.
Okay.
But certainly, yeah, we have, encoder feedback on the elbow, so we could convert that into a degree measurement and based on that calculate how much the height changes.
Okay. One thing I want to let you know, look out for is I would suggest double checking, like have some known variables measured by hand. Like if it's at 45 degrees angles, we know it's at this height. And so you can check your calculations. Thank you.
Mm-hmm. Yeah.
Oh, I think I should play the video real quick. Oh, sorry.
That was low.
He didn't see where that one went. Anyhow, I don't need to play more, but they did a grouping of the shots from that video. Who's taking this one?
Navia, you want to take it?
Oh yeah, I thought we were all Trey, but yeah, I can go for it. So as Mr. Brownie mentioned, Justin and Trey were shooting these rings towards that wall to see around like where they group at. And this is a diagram of around the like the area that the rings tended to group around. So the grouping tended to be at an arrangement of around 8 feet high. So, or did I get that right? Is it 8 feet high? I'm sorry, I wasn't there for the testing.
Distance 8 feet. Yeah.
Yeah, so it was about 8 feet, and the grouping was about like a 3-to-1 arrangement. Having the grouping is really helpful because it helps us identify where the rings tend to go, and that also allows us to determine how driver control needs to change, and that's also something that could be input into a launcher like equations and modeling trajectory if we know where we expect the ring to generally land.
So to be clear, those were repeated shots without changing any of the articulation of the robot. So this is the natural variability that we've got at the moment in the ring shooter.
I have a question.
Mm-hmm.
You tested how many balls in your statistics test to see the inaccuracy of it, or the accuracy? How many tests did you run, like shoots wise? And did you guys modulate the distance from that the robot is standing from the wall? So
this is you got to realize that this thing was put on last Tuesday, not even mounted on the robot. It was mounted on the robot sometime this week. So this is very early. When they were doing these tests, it wasn't to determine the performance accuracy so much as it was just a sanity check to know that we could so that the robot could achieve sort of the minimal flight characteristics that we need in order to get to the distances we need. So it's very early on in the testing phase, and they haven't really got to what I would call statistically significant size of tests.
It's really good though, with what you guys have, and I think you can work a lot with that. Yeah.
I was personally hoping it would be a little bit more accurate than it is, but because the size of the target that they're going for is pretty thin. So, in other words, there's no inaccuracy here from actually trying to calculate where the target is. This is just leaving the launcher pointed at the same place the whole time, and there's quite a bit of variability there. So.
Do you think that is because of the mount is not tight, or is it, how do you have it all mounted? Is basically what I'm trying to get to, because I'm thinking that's where you're getting some of your variables.
I don't think we have a photo of the mounting at this point, but yeah,
Okay.
There's going to be a video coming up of a slow-mo that will sort of hint at maybe some of the stability issues that might be causing the variability.
I'm thinking that's where you're getting the slop basically, is because if you have a small little hinge and you have a big mass there, yeah, you can have lots of variables just because of that fact.
Yeah, the other thing that occurs to me is that you might want to put identifiers on the little rings, and when you shoot a particular ring, keep track of which one you're shooting and see, because I think there might be some variability in the actual rings themselves, because they're not perfect. And if they're slightly off size, or maybe the material's a little bit more spongy than the other ones, you could get quite a lot of variability just there. And if you, let's say, shoot the same ring over and over, you're at least removing one variable.
Yep. You can see that there's 3 groupings in this slide, and there's this bottom tail where things go really weird. So it's I don't know if you can see the cursor, but some of them are pretty vertical, and but there are fewer in the lower right quadrant, and it seems to be a consistent misfire, but they haven't figured out why yet. Somebody gonna do the annotation on this slide?
Yeah. So this is a video of us swapping out the previous gear ratio, which was a 3-to-1 for a 1-to-1 on the flywheel to achieve a higher speed. With that, the trade-off is that there's less torque on the flywheel, which means it takes a lot longer to ramp up to full speed, which in this case was about 10 to 15 seconds. And so Trey actually discovered a problem with the 1-to-1 gearing where the ultraplanetary motor config has to shim it. So here's a video of that.
It's going over 4 feet.
So it's the same thing. The testing of the one-to-one speed of the motor is that it might be a little bit of an overkill. It clears the 4 to 8 foot foam board when it's launched a maximum, but the other issue is that the angle of the rings were launched at made it hit the ceiling, which they're not supposed to do. There's a maximum height which the rings are allowed to travel, and that's 5 feet, and they're not supposed to go above that. But the only, but a good like result of this trade-off is that this might be a little bit more accurate. And then I believe this is the grouping of the rings, like once they're shot out into the driveway beyond the foam board. There's a driveway right behind the foam board, and this is how the rings tended to cluster as they were shot beyond it. And then Justin worked on prototyping a new transfer system called Pancakes. It's codenamed Pancakes, so honestly, I have no idea what it refers to because it is a secret, but it's a pretty extreme reach goal that hasn't really been tested yet, and there's intentionally no images of this system on the slide below because, you know, it's supposed to be a secret.
So on Sunday, we actually started translating all of the, sorry, did someone say something?
No.
All right. So on Sunday, we started translating what we wanted to, what we had in the calculations to actual code. And the first step of that is to get a velocity PID loop on the flywheel motor. So yeah, what that is a thing to note in terms of variability is that we didn't have a velocity PID running when we were doing the test. So that might have reduced some variability after it's, you know, properly tuned and all of that. So we use this tool that you can see here called Ftc Dashboard. It's just a little web interface that allows us to graph out different variables and things like that. So in the green line, you can see the target velocity that we want to reach, and the blue is the current velocity. And so this is our remote coding setup, and we use GoToMeeting on the laptop that you can see. 2 webcams are looking at the robot, and the robot's webcam shows up on the dashboard that you saw on the previous slide. And so I can control that the laptop via, you know, remote desktop, and the laptop can control the robot over Wi-Fi direct. So.
Okay, so on Monday, Trey assembled a slow-mo video of 10 launches back-to-back to look for how much variability there is between each of the launches. This was using a 3-to-1 gearbox ratio. So around launch 5, there was some ring damage. I think someone brought it up earlier that the rings might have a little bit of changes in their structure and things like that. And this was the case here, even though the rings didn't have any changes previously. The fact that they encountered some damage is a little bit of a problem because we don't really want them to do that as we're launching. So if Mr.
That video is a thing of beauty.
That was
So-
10 different shots, but it was a handheld camera.
Slow-mo is great.
Yeah, the slow-mo was pretty helpful because it showed us something about the audio. So the audio actually reflects the acceleration of the rings as the fin rubbing. So between the 2 flywheel plates, there's a series of like little fins. And as those rub against the rings, that rubbing decreases in frequency as the ring ends up catching up to the flywheel's tangential velocity. So that kind of shows how, you know, like the fin rubbing decreases in frequency. And that's what we were hoping to achieve with this launch anyway. We wanted to check how consistent it was, and we found out that it really wasn't as consistent as we hoped it for. But we also need to get more analysis to see if we're actually reaching the full acceleration. And this part of it requires a higher frame rate. So, you know, slow-mo might not be the next one that we end up using as we try to check if it's reached its full velocity or full acceleration.
And that wraps us back to today.
So hopefully we plan to be back on March 13th if we don't end up having a competition. By then we'd likely be done with our first qualifier, unless that does end up being our first qualifier. And we'd love to present our robot as well as our progress and how everything ended up working out that day. Here are some links. So ever since our meeting with you last time, where we presented our ballistics calculations, we ended up updating the calculator. As Mahesh mentioned earlier, Jose built a Desmos calculator to model the trajectory into an equation in the calculator, so we could visually see what the arc looks like in a parabola. We also ended up posting on our blog. I think Mr. Browning wants to show the calculator first, so y'all could see that.
Apparently, it's trying to do it in a different window. I'd have to switch windows. We'll just share the links via in the chat, I guess.
Okay, gotcha. And the next thing we did was our corrections post. So after our meeting with y'all, we ended up having a couple of days where we reflected on our calculations and our equation. Even though our equation didn't have substantial change, the way that we got the remaining calculations ended up changing a lot. And there's one thing that I wanted to point out about that was a focus of the corrections post. So one thing that I think we didn't explain really well to y'all was why we ended up using the summit for the trajectory. So we know that the launch of the rings is modeled in a parabolic arc, and we aimed for the goalposts to be at the summit. So part of it was to reduce variability and error, but another reason was because of how we could derive time from it. So if we took time as a fixed variable, that would streamline our processes for finding the rest of our calculations. But in order to find time as a fixed variable, we needed to launch a ring at 0 vertical velocity. We needed to do this because we knew that for any shot that crosses through the goal with 0 vertical speed, the ring needed to have an initial upward velocity so that the acceleration brings it to 0 vertical velocity at the point that it reaches the height. So no matter how far away the robot is from the target goal, target time in this situation is controlled purely by gravity and vertical distance. So finding time at 0 vertical velocity allowed us to better model an equation for the summit of the ring's trajectory. And that's pretty much why we ended up choosing the summit. So I just wanted to clarify why that was the decision that we created. This also allowed us to create an equation for time, which also helped us streamline our equation. So presenting to you guys helped us verify the faults in our equations, as well as how we could improve them, and particularly how we could improve how we go about describing our equations. So yeah, thank you guys for last week's feedback. It was really helpful in our next steps, especially as we streamlined and fine-tuned our calculations. And the final link is to the slow-mo launcher, which is the flywheel launching rings at a slow motion. Also, we had one question to ask. We are renaming our launcher to something a little bit more catchy. We have 2 ideas so far. The first one is Ring Slinger 9000, and the other is Flywheel Launcher. Whichever one you guys feel has a better ring to it would be great. And also, that was an incidental pun because we're launching rings. So whichever has a better ring to it. Yeah.
It's always best to explain your puns.
See, I got the Ring Slinger. I like that better than the other one, but you got to go 9001 because you have to be able to say it's over 9,000. You have to go get the DBZ reference in there, man. Come on.
Well, I do
Go
like
for a
things.
show of hands. What's the first one again?
The first one is Flywheel Launcher. Pretty simplistic.
Okay, so Flywheel Launcher versus Ring Slinger 9000. Who wants
Yes.
Flywheel Launcher? Who wants Ring Slinger 9000?
My hand's up.
There's your answer.
So we have a winner.
Ring
Oh, and
Slinger.
also the quote of the day, which I wanted to share. So after we ended up talking with y'all, we realized that we needed calculations for muzzle velocity and RPM, so that we could have extra information about how we'd want to model our launch, as well as how we could adjust our motor. And so I said, theta, there's more to the world than theta. And Mr. Veroni put it in the slide as a quote. And yeah, that would not have happened without y'all's insight. So thank you for our the quote of the day from last week or this week.
So that's it. We're done unless anybody has any sort of advice on how to further improve the stability, or if they saw anything weird in that slow-mo that we haven't seen yet.
I have some experience with this. When I was in high school, my FTC competition, I was focused heavily on the projection curve, and I only figured out until when I got to college of what the answer should have been. If I'm correct, you guys have done the calculations to model it correctly, right? The curve of the projectile rings, right?
I think they've finally proven that they've got the ballistics down pretty well. The big problem is that this is not a purely ballistic type of shot. It is those rings have maybe slightly a frisbee type of effect. So there's some aerodynamics going on, and maybe even some lift, and that's probably more complicated and more modeling than we really need to do. Last week, the DPRG members talked the team into look at different ways of what was the term called? Design of experiments, DOE. Different ways of determining sort of, in other words, our equations will probably be their starting point, but then they're going to have to go into actual real world performance and then figure out how that impacts their trajectory calculations.
I couldn't hear. Did you guys by chance have a sensor on your robot that can detect the distance it stands from the wall? The nearest wall it's standing from?
Yes.
Okay. All right. Do you guys plan on focusing more on improving the code for the robot or improving the accuracy for the robot in this next month to come?
You gonna answer that, Mahesh?
Well, it's not even really about improving the code at this point. It's just trying to get it made in the first place. But after we reach that point, we can worry about things like drag or lift and stuff like that, and fine-tuning the different constants that we have written in order to sort of minimize variability. But right now, it's just trying to get all this stuff into fruition and bring it into the practical world. So that's the priority.
I would highly suggest getting as close of a approximation curve that you can and putting that quickly into the code of the robots. And then so that your robot only needs to measure the distance from the wall and keep the velocity constant, so that all you have to do is change the angle and have maybe preset buttons like to toggle between the different heights that you want. I looked at the competition, and that way you guys don't have that much human error on competition day. You know, you can work with the somewhat flaws, know what flaws you have, work with them as best you can, and think what's the easiest way to work with them into our favor, you know, so that that's round 2 for regionals. You guys can you can improve upon that and maybe add drag, because that level of mathematical calculations probably high, like super high up there with college physics, and it might take you a long time. Who knows? But it's really good right now. But you guys are very close. That's my advice.
Gotcha. In terms of having buttons preset for 3 different goals, I think we're just gonna keep going for the top one. We can have that in there, but the most points are from the top goal, so I think that's gonna be our priority.
Okay.
And I think what might not have been clear is that they're going for completely autonomous targeting. So the robot knows the distance to the target, it knows the height of the target, and it knows left to right where the target is. Hopefully using vision. That part's not developed yet, but that's part of their goals.
Yeah. So you were
Kareem,
sorry.
You mentioned the frisbee-like behavior of the rings. Does that does the lift change depending on how much spin the ring has?
We're not there yet, and we don't have any ability to control the spin outside of how fast we're shooting it, because it's set by that launcher, right?
Have you guys tried reaching out to maybe local physics professors in your community to help you with the calculations for the drag, lift, and all that.
Yeah, that's you guys. Get to it. No, that's a good idea. We should follow up with academics. Right now, we're having a hard time reaching people, and it's just everybody's discombobulated by the epidemic or the pandemic. So
True.
Do you guys happen to have any recommendations on physics professors that we could reach out?
throw somebody under the bus.
Let me dig one up.
You already have a launcher, so I'm thinking try to calibrate it and understand how its behavior. So I guess, yeah, another round of improvement. It might be better to understand the system and yeah, you have something to. I mean, calibration is an important part of instrumentation, right? So that's where it's a good time to do that.
I would like to recommend you reach out to a professor I know at the University of North Texas. His name is Dr. Weathers. He's a professor that goes out of his way to show demonstrations during class. He's always helpful during his office hours. I highly suggest, I'm putting his name in the comments on the chat box with a link to his information page. Wonderful person. You'll get exactly what you want to know from him. Thank you.
Gotcha. Thank you. And would you be all right if we reference that we like knew of him through you?
Yes, my name is Webster Brown. You can definitely use me as a reference. You can even CC, if you want to write an email to him, you can CC me if you want to. My email is.
You don't want to say it. It's you can. Is there a way to DM it? You can put it in the text and then we'll remove it because this is recorded.
Okay. I'll just send it through DMs. Thank you.
Hey, Kareem, did you ever look at skeet shooters? Are they consistent in what they do with clay pigeons, or
Yeah, they looked at skeet shooters very early on. Those aren't nearly as consistent as what we're going for, probably intentionally.
Right. Yeah. I guess you want some variability there. So
yeah,
if it's a sloppy design, that's perfect.
Exactly.
Yeah. Okay. Yeah, I was kind of curious about that. We being from Texas and all, you know.
That's right. Yeah.
Is there a way to add a nozzle, like I don't know how it's muzzle, right? I mean, it's something that restricts the motion after your spinning and speeding up. To I don't know if it's going to make your final target more concentrated.
So. Let me present that again real quick.
It might cause drag if you use a muzzle, and you'll have problems with the space issues that FTCs require you to have it be within a 18-inch by 18-inch by 18-inch box, right?
Yeah. Yeah. So it basically has a muzzle built in. I don't have the image loaded right now, but there's a wall that goes around the outside, right? And that's what the ring is compressed against. At the very end of that wall, it continues straight past the point where it would come away from the flywheel, right? So at that point, it's no longer engaged with the flywheel, and it's just acting as a guide. So there's the plate underneath, there's a plate to the side that pretty much constrain. I mean, I don't think that we would be getting as much accuracy as we are right now if we didn't have that in there. But there are limitations on how far we can go out with that. Plus, if it was actually hitting it, it's that's a spinning disc, and that could actually create more variability if it's not already sort of walking its way along that wall.
Yep. Hey, Kareem, did you weigh the discs and measure them and for like I don't know what it would be,
variance,
specificity, kind of being out of round because I'm.
Yeah, no, we haven't profiled the discs themselves.
Yeah,
and I can tell you that they seem incredibly consistent. They're clearly injection molded foam. They all seem to have the same dynamics, but we haven't done a really close measurement on it.
Yeah.
And in a way, it sort of doesn't matter because we're not in control of the rings. We got 20 delivered to us, and there's going to be a different set at any competition. And all of the other teams are in that same situation. So whatever the rings are, we got to live with it as, that's what we got to make as accurate as possible.
Yeah, the only thing I could think, well, that's pretty complicated, but if you have a ring that's heavier, it may not go as high. So maybe you could add a little extra velocity or spin to compensate for that.
So we're
yeah, Ray has a point.
We're gonna weigh each ring as we take it in. Yeah.
Well, he has a point that you might want to have a variable to account for that, so you can literally adjust for the rate of the rings. So yeah, and I was having a variable that you could plug and change on the fly to account for that.
Karim, you laughed at that, but a load cell is pretty accurate, and you can weigh it on the fly as it comes in, and get a thing on it, man.
I wasn't laughing at the concept. I was laughing at us doing it.
Okay.
I mean,
yeah, but you guys are in Texas, right? And in Texas, don't you guys weigh your bullets before you shoot them?
Oh, I think that's part of it. It's so many grams for gunpowder and
so. When I think about maximizing variables, I think about maximizing the variables that give results, not maximizing the number of variables.
Oh, that could be a thing.
Now, these guys are probably going to tell me I'm a little full of it, but I would think, though, if you took those 20 rings and and weighed them all and kind of measured them all, I would bet you could bracket that set of information to make it close enough to hit that hole. It's not like you're hitting millimeter accuracy here. I bet you make it close enough if you just do a little, just measure them all, take some means, take some averages, all those sorts of mathematical terms you want to use on them, and be able to bracket that around there and base your calculations on that bracket. I bet that gets you close enough. I mean, I don't know. You got to try it, obviously.
It may be the secret sauce,
Of course, it's all going to change as the rings wear over the season.
Oh, it is going to change, right? Exactly. Yeah. But at least you can have an idea of where the starting things and all that kind of stuff goes, and get you a starting point, so you're not stabbing. I call it shooting ducks in the dark. At least you can put a stake in the ground, so at least you know where you're started. So then you don't know where you started. How do you know if you made any progress, right?
I'll push back a little bit and say that I think it probably doesn't matter. For a very technical reason, and that is that the gravity portion of it doesn't matter how much it weighs, right? It's got nothing to do with it. The mass has nothing to do with the rate at which it descends to the ground.
Wasn't it Newton that shows that?
Yeah.
Now, the air friction might be another issue, but
air friction is a different thing, but we're not there yet, right?
Yeah.
So, but in terms of the mass, it's got no impact on that. The only thing it would have an impact is potentially on the amount of speed if we were sort of at the limit of the way the ring, the flywheel could impart momentum to that ring, right? Mm-hmm. So if we're close to that point where it would vary from one ring to another, but I think that there's so much momentum in that ring, in the flywheel, that versus the weight of those rings, that we're not really there. They're all going to exit with about the same velocity.
I'll take that pushback, because I mean you are 100% right. The gravity and the mass doesn't matter, because the way it's going to fall on it's going to be Newton's a pretty good guy like that, right? And
Yeah.
the air resistance, although you need to factor it, I don't think that's going to be over the short distance you've got going on there. I bet it doesn't matter at all.
Yeah.
Or not enough to make it miss. But I don't know. We got to play with that. What do I know? I can't get a robot to run around on the ground. So what the hell do I know?
Well, cool. Let's hear it again for Iron Rain. It's always great to have you.
Thanks, guys.
I think these
Yeah.
young people are
It
great.
took up way more time than we should have again, but appreciate it.
And with any luck between now and our Saturday, March 13 meeting, you guys will have some great progress and we'll have a cool presentation. So we'll touch base as we get closer, Kareem, and pencil it in or pen it in as it takes time.
You saw that there was one competition date, and
Yeah.
while we had preferences, we can't. We're not in control of actually being assigned which one we're assigned to. So,
well, just let us know, and we'll. No, thank you.
Thanks. All right.
Cool.
Thanks for having us.
Hey guys,
I have to head on now.
Thank you. Thank you.
Anytime.
See y'all.
Good luck. All right. So swinging around to, I almost thought for a moment there that Harold was going to challenge Iron Rain with like adult members versus high school members, but I'm glad you didn't do that, Harold.
Dude, I don't want to lose. I don't want to lose that badly. Trust me.
Yeah, that would be a humbling experience, I'm afraid.
Oh yes.
All right. So who would like to talk about what they've been doing last week? And
I'll say that Chris is right again. By the way, if he's on, I'll be happy
go
to say
for it.
that.
He's there.
Chris,
Patiently waiting.
I'm usually
I'll put a
right.
link up. Oops, sorry.
You're right again, believe it or not. What you're seeing, where am I? I think this is what I need. Yeah, what you're seeing right there is the joystick controller with the baked-in ROS joystick node that I didn't know existed till about a week ago, even though you tried to tell me it did, and I didn't listen to you very well. So you're right, and it works really well, does exactly what I wanted to do. And actually, it works too well because I've tried to get away where I could get I started playing with this thing called a ROS bridge or ROS. We're using the ROS web tools. If you go to roswebtools.org, there's lots of tools and things out there, and there's a few of those that expose the ROS message queue as a WebAssembly. I mean, a WebSocket port, so you can send messages and subscribe to stuff on it and see all the stuff coming out of a WebAssembly. Not WebAssembly. I got WebAssembly on my head right now. A WebSocket. So then at that point, I'm sending JSON back and forth to whatever I want to do for monitoring and subscribing to nodes and subscribing to topics, and I'm seeing it on a web interface for controlling the thing. And so, what kind of fun things can you do with a web drawing up user interfaces with web pages? Some of it's pretty easy, pretty simple, and it can be. Knowing me, it's probably not. Put myself back, and so I started playing around with that, and I got really upset because almost all of them don't work on Foxy, which is the latest ROS 2 version, and the ones that were working were based in Node, and just as it just failed right off the bat. And I said, whoa, well, let me do some testing. So I fired up the Node version of this, fired up a standard talker that it just puts out hello world once a second with an ever increasing count on it, so you can see messages come across. And after about 20, 30 messages, that Node web server just crashes dead. And I'm like, this is a bunch of crap. So I can't use that. And I did find a pretty old version of some .NET, and I said, well, can I do it differently? I did find an old version of a ROS2.NET thing from 4 or 5 years ago. It compiled. I haven't got to run it yet, but if I can get a hold of that and fire up a web socket, then I'm like, that's kind of cool. So I started exploring that. I didn't get very far with it at the moment, but I started playing with that, and I think hopefully that'll bear some fruit, because at that point, my robot becomes a web server as well, to throw things out, and I think that's neat as all get out. I think that neat as all get out, and so that's kind of what I was playing with the last few nights on my Twitch stream, that kind of thing. And I'm thinking that the .NET thing I finally actually compiled, if it actually works any at all, I need to get it on .NET 5 because it's .NET 3.5, and there's lots of fun things that don't exist back then that I really want to take advantage of now. And so that's kind of I think that's where we're going to play for a little bit. And I need to get me another node up to be able to drive this thing around again. At least I'm making headway this time instead of just being stuck. And I got a plan. I got designs and graphics and words and stuff and things, and yes, I have plans. So, you know, at the very least, that's some kind of progress, I think. That kind of thing. Cool. Anyway, believe it or not, that's about all I got this time. You know, I'm not going on for hours. I'm gonna surrender the rest of my time to Murray because I'm figuring he's gonna need it with PID loops. So that kind of thing. And I brought it up.
No.
Harold, mind if I ask a question first before we move on?
Ask away.
What are you using for your server?
As far as what do you mean server?
You said you were using a server, correct? If I heard that right, to run
No,
some.
I'm using. I've got I've got a couple.
Raspberry Pi.
I've got Raspberry Pis on one thing, but that's not really on that robot. On this robot, I'm using a Latte Panda, which is a full Windows. Look at that. Am I showing stuff? Yes, I'm showing stuff. If you will see right there, this blue thing, that's a Latte Panda, which is a full Windows box with an Arduino attached to it. And this is basically the head of the robot that's going to be. I'm working on making a Teensy to do all my real-time stuff. Yeah.
It runs Windows?
Yeah, it runs Windows. Yeah.
Oh. And what's it called again?
It's called a Latte Panda. Latee Panda. Panda.
Latee Panda. Thank you very much.
Yeah, you're welcome. And but as far as it goes on here, I don't need a real server. All I need is a process that can serve an HTTP endpoint. And in that case, there's the .NET 5 or Core 3.1 or Core 2.0 all have built-in servers. You .NET run, boom, connect up to the point, and you're running. I mean, it's just that hard, or it just isn't that hard. And so that thing is just throwing it out there. And then so the idea was I might have nodes local to my Latte Panda or local to my lab machine where I'm watching the raw nodes and traffic that's going around doing all the things. And the interface could be a publicly facing kind of thing where if somebody's got their browser on the phone, I say browse this address, and you can see what the robot sees and maybe throw up information in there, because that'll give me some graphical stuff. I could probably do some graphical things as well as just numerical junk that's flying across there. I thought it'd be neat if I could make that happen. You know, that sort of thing.
Okay, cool.
Bye, Mr. Grant.
Yeah, good to see you. Hope you're feeling better soon. Thanks for sharing the link on the YouTube, Ron.
Okay, hey, Carl,
are we supposed to meet?
What?
Carl's in a tin can.
Is this any better?
Oh, a little.
A little?
Ron, are we supposed to look at this link?
Yeah, Dave. Sure. Sorry, I've just been crashing early. I'm still messed up, sick, whatever. Getting better, but anyway.
Yeah, Ron, you had shared some cool stuff that you've been working on. I think is this just towards the outdoor robot simulator you were working on?
Oh, sorry, Carl. I can't. Hang on.
Hey, Ron, go, man. I am shutting up now. You're on. I think you're taking point before you get out of here.
Well, anyway, yes. So I've been working with a Open Dynamics engine, which David Anderson's former neighbor wrote the program about 20 years ago. in the C++. Anyway, somebody did a really nice Java port of the Open Dynamics engine, and it's probably 50,000 lines of code. 3D physics simulators are nasty complicated. That's all I can say. I understand maybe 10% of it. So anyway, but using this Java port, what I've been able to do is create a processing library, of the ODE code, and then I'm able to create Java code to create simulations. So what you're seeing in this simulation is just sort of a little compendium of a few things. Oh, did I send the right link? Oh, YouTube says, oh.
No, it turns out it's the right link. It wasn't anything inappropriate.
But yeah,
YouTube flagged it as inappropriate. I don't know why.
Oh, anyway, I set it up that way because I didn't think people can't leave comments if you leave it for children. And the funny thing is, since they implemented that, you don't see any more nasty comments because children were leaving all the nasty comments on videos. So it's really ridiculous, except I suppose some children or adults would be offended by what children write. So anyway, but I like to be able to have, sign in to confirm your age. I could probably change that. And maybe it's, that's weird. Maybe I set it up too restrictive. Anyway, okay, so back on the simulation, the thought is if it looks good enough and it's not too complicated to write a robot controller, it might be something fun to mess with, sort of like LFS, but in 3 dimensions, and targeting a couple of our contests, like outdoor contests, and also maybe 6CAN or something like that. But one thing I do need to get is data as far as, realistic simulated GPS data. And I'm sure somebody like David Anderson could probably clue me in on the behavioral characteristics, or many people probably could, of your typical GPS, without going to, RTK or any of that stuff. So anyway, but my thinking is, well, if I can do that, I've got the visual capabilities to simulate, robot point of view, including when the robot's driving over nasty terrain, the camera's bouncing around. So I'm thinking it might be kind of cool, but we'll see. My goal is, okay, pretty it up a little more, and if people get interested in it, great. If not, I'm probably not going to invest the kind of effort I did into LFS's API documentation, but I don't think it would really be necessary. If you want to dig into ODE and create your own little gizmos, sure. But one thing I did notice, that at least on my intermediate level desktop machine, that I was able to implement kind of a time warp, and I'm seeing frame rates of 500 to 600 steps per second. So that's been kind of handy. Anyway, that's my story. Anybody have any questions? Otherwise, I'm sorry, I'm not gonna last long.
Well, I asked my usual question. You probably know what it is. So remind me why you're not using an off-the-shelf simulator?
Well, I was disappointed in the frame rates. I didn't see that I could get 600 frames a second out of, was it Kibitzing? So the hell with it. I figured, oh, well, I can hack this together and also make something that sort of fits into DPRG. So,
yeah.
But anyway, I do like the ability to speed things up. So.
Yeah, I think WeBots, and I haven't had a chance to really get into WeBots much, but I know it's much faster than Kibitzing, because even just a trivial, even one of the included trivial demos, which doesn't have much going on. I mean, it's going, I don't remember the number, but many multiples of real time.
Okay.
Where in Kibitzing, even if you have almost nothing going on in your robot or environment, it still couldn't get beyond, 2x, 3x, maybe 5x real time on my machine, right? So versus, again, VBots for a similar test, again, was doing, tens and tens of x of real time. So VBot's much faster. I don't think you can get your 600, x of real time or whatnot, but definitely much faster than Kibitzing.
Okay.
I agree. It's nice to have something that's much faster than real time. I agree with that point. Yeah, so I need to spend more time in dbots because I think it can deliver, maybe not to your expectations, but it can deliver more than Kibitzing.
All right, well, neat. My interest here is really kind of self-serving. I mean, whether I'm interested in, playing with the simulator or playing with the dynamics engine and learning more, about that, so anyway, that's kind of my goal and interest. And also I like processing a lot. And so my main interest is really to bring the ODE library to processing, since all the work's already been done for me. Russ Smith wrote the dynamics engine, and then another guy named Tillman, I don't know his last name, Zanacek, something like that. He wrote the port, which was, I think, a lot of work. I mean, it's obvious that he has language knowledge in both Java and C++, far, well, that's not saying much, far exceeding my knowledge. So he, and there's problems, and some things don't work, and I think some things might have been broken from the original implementation. But nevertheless, it looks pretty good. So my goal is I'm going to bring ODE to processing, because there's no real 3D dynamic simulation. A real nice 2D simulation or 2D physics engine, and then there's also a soft body simulation, which is pretty cool. But ODE has got some really neat features. So anyway, that's my story.
Ron?
Yes.
This is Donna. So what does ODE stand for again?
Open Dynamics Engine, and I'll put, it's just ode.org is the original website for Russ Smith's Dynamics Engine. And then from there, you probably could search, YouTube, you'd find some videos. And then the port to Java, I think it's ODE4J. You could probably just look for, ODE, and then I usually throw in like physics or 3D, and then Java, if that was your interest. But in C, if you're interested in doing something in C, then there's different avenues you can go in different environments, Visual C or whatever, or any, a number of environments where you could use the original library code. It's amazing the performance of the Java code is pretty good. But then again, it's been a little while since I've played with ODE, where I used Pascal, which had probably a pretty clean interface to the ODE DLL. So it was probably fairly efficient with the object Pascal, which was very fast, and that compiled to native machine code. But anyway, it's looking pretty good as far as performance under Java.
Okay, thanks, Ron. And then Open Dynamic, the Open Dynamics engine and the ports that you mentioned are all open source, I assume.
Yes.
I assume, right?
Yes. Okay. Yes.
Okay.
Yeah.
Great. Okay. Thanks, Ron.
Yeah, and it's neat, but it is kind of complicated. But as Russ Smith points out, the original author, look at the examples, because you can read all the reference manual, but you kind of need to see the examples to understand, how to incorporate, the dynamic objects that have really no physical size with the objects that do have physical size that are used for collision and so forth. And it's interesting, and I think it's really about the only open source free kind of physics engine out there of that significance. You probably get to PhysX or some of those, and there's been a lot more development work, but you don't have access to the source code, and so, which is sort of fun, because you can kind of get in there and realize how little, in my case, how little I know. So anyway, sort of humbling.
OpenDE is both 3D and 2D compatible, or what?
You could probably create things that would be constrained. Well, it's really designed for 3D.
Okay, I see.
Yeah. It's I would say you could probably create some 2D simulations, but overall it's designed for that purpose. And so really the main components, you've sort of got the physics side of things, which deals with just masses and their inertia, But then of course, the complicating factor is you introduce, not only do you introduce bodies, like a cube, for example, has a physical presence. So when the cube hits the ground, it contacts the ground in a certain way and creates torques and forces on the cube, and if it's bouncing off 10 other cubes, then it's quite a problem to solve. And then beyond that is when you add mechanical linkages, you can add hinges and ball joints and sliders and all sorts of things that constrain the system, and it gets into some pretty interesting problem solving, but that's taken care of. But it takes some finesse too, as far as when you create systems, they can become very unstable, and there's tricks to making joints spongy or soft in order to help the system maintain stability. I mean, it's amazing how you can make something that just rips itself apart because its parameters are incorrectly set. Interesting.
Yeah. Thanks, Ron.
Sure.
I've been gone for 2 days, so I can see something different.
Oh, sorry. Well, that's the end of me. So if no questions, then that's done for me. And I'll probably sign off here in a couple minutes so I can have a good coughing fit. I had pneumonia through the whole month, so pretty bad. They said it wasn't COVID, but then I had that coupled with pericarditis, which hurts like hell around the heart. And so I was pretty much amazing to have no willpower to do anything. I think I wrote some days 1 or 2 lines of code or nothing. And that's kind of not like me. So anyway, but I think I'm recovering. So, but I'll now, sign off and have a good coughing fit.
Get better, Ron. Rest that voice and get better. We'll catch you later.
All right. Thank you. Nice seeing everybody. And I'll watch the video after. Bye.
Bye. Man, rough times. Okay, so who's next? Because I think we're almost getting into this game where somebody would go tag somebody else to just try and call them out and get them started off.
I'll go next if it's okay.
Chris. Ron was going to tag Chris, and Chris wants to go anyhow. So how about Chris and then Donna?
All right. I'm going to just switch to my phone as my camera. So let me, because I have something sitting on the floor. So let me mute this guy here. And unmute. Why is it giving me echo? Okay. So let me just see if I can figure out this thing here with my phone. Oh, can you guys see this?
Looking good.
And you can hear me. Okay, good. All right. So I think this line following course, I think I had this Zen course down last week already. I don't remember if I had the full circle or just a segment of the line. Either way, what I've done since then, and for those who weren't on last week, again, I'm trying to use line following as a way of getting my robot to traverse a very repeatable trajectory and then collect data along the way and look at the data and calibrate things and optimize things and so on. And I have a little test track in my room here. The idea is to have I have a longer track, out there in the hallway that isn't all that long yet, but can be quite long when I decide to finish it. So for now, I'm just using this oval here as a test track to work the kinks out of my software. The main thing I've added were two of these orthogonal black lines, and the robot's actually positioned right now at exactly one of those lines. And where it's right now is basically.
Chris, should we be able to see what you're doing?
Oh, I thought you could.
Yeah, well, so David, he's not presenting, which means if you can find him in the tiled view and you can make the screen that
Can
you
it-
want full screen.
Yeah,
Yes,
just
I
change-
do. I do see that, but all I see is Chris and the TV monitor on the wall behind him. I don't see
Sorry,
the
I'm in
floor.
there twice. I'm gonna turn the camera off on the one that you don't want to look at. Find my second login. Sorry, I'm logged in twice.
Well, the
You're
second,
talking on the one that puts you visible, which is the one you just turned off.
Dave, if you can't see if you can't see the second one, you may need to change your layout so you can see more people, because the default I think is 9 and there's 16 you can turn it up to.
So
I can see the second one, but it's black.
That is
Well-
odd.
So I'm presenting now, and you should see my screen. And basically, this is the view that I use, not for the recording one, but for my own box. And it lets me see everybody, lets you see everybody at once. So like here's Chris's blacked out screen, and here's the one of his floor. So if I wanted to make that full screen, I would click this little push pin.
Yeah, pin it.
And
well, there's some other problem I'm having. I have two Chris screens. One of them has a little icon of Chris's head. The other one is black.
No, you shouldn't. Well, the black.
It's my problem, Carl. If you'll leave this up, I can just watch on yours.
Okay. All right, we can do that. Here we go.
All right.
Must
So
be
I'm
Linux.
gonna-
Works
sorry,
in
I think
Windows.
maybe it's my phone. I don't know, but I usually don't use the phone. So David, so you can see this now. Maybe so I've added 2 markers here to my line following course. The robot's positioned right at 1 marker right now. I call that my XY, theta is all 0. That's call that my origin. And then I have a second marker that I'll explain in a second. So again, the idea is to run along this course, collect some LiDAR and other data. I don't have the LiDAR mounted yet. So far, I've been mainly looking at my odometry, trying to calibrate that properly, but mostly at my IMU. And I have 2 IMUs going on right now. Really, I should say just the gyros is what I'm using. I have 1 IMU built into the Romy control board, right, which is this thing with the blue LED. Those of you who have a Romy, and I think it's just one of the guy, right? There has an IMU on there, and on top I have the BNO 085. Right now connected to a Qt Py. And then the Qt Py to the Raspberry Pi. So it's a little bit convoluted setup here, but it was just convenient to do it that way because I can carry this whiteboard around and run a few other tests. But so I can collect data from 2 different IMUs, and the whole idea of this setup. And I'm gonna have a couple questions for you guys to find out if that's really a good idea. But what I'm realizing is, or what I'm thinking is, this is a potentially a convenient way to calibrate a few things, including and especially odometry, right? Where usually the way we do calibrate odometry is we run in a square, right? And there's some famous published papers on that, and you run in the square, and then you end up close to where you started, but not exactly. And you look at the difference, and you take that into account somehow. But what I'm doing, I figured, okay, if I do this on this circular course, and it doesn't have to be the shape, of course, right? But as long as it's something that gets me back to where I started, what I can do is I can run 5, 10, 100 sort of loops here on this circle, and I can make it stop. I can do a very controlled stop back at the starting point. And that's what this line is for, right? This line tells me when I'm about to approach my starting point / end point, because that way I can slow down and do a very controlled stop. And I will know for sure that by the time I stop, I'll be 100% aligned to the black line on the floor. And I'm going to be exactly where I started out, right? Without much doubt. So I run a couple loops around the circle, right? And then I can look at my odometry and look at the error, and then make adjustments to the principal, parameters based on the error, meaning wheelbase is probably not the exact, number and my left wheel diameter, right wheel diameter. I mean, those are the three main parameters, or only parameters really, right, that you can calibrate for. And what I'm thinking of doing, I haven't done yet, but once, so I run around in a circle here a couple of times, right? Collect some data. In fact, I'll show that in a second in action. But now with that data, and I collect each and every odometry sample that I take, which I do at 100 hertz. Okay. What if I then process this data offline, right? And basically, tweak one of the calibration parameters, or tweak all three of them systematically in a loop, basically, or even just exhaustively explore sort of a range of parameters there until my end result is such that it gives me an XY of 0, 0 and a theta of 0 when I'm back at this point. I'm not sure if I'm making myself clear, but once I show this in action, maybe it becomes clear. But that's sort of one question to the group there. Wanted to find out if that's a good way of calibrating.
May I offer an answer?
Sure.
Chris, that'll work fine. That really is the UNB mark calibration. And it really doesn't matter whether you drive the robot around and have it stop where it thinks 0, 0 is and measure the distance to the real 0, 0, or if you drive it around and have it come to the real 0, 0 and then ask it where it thinks it is. Those two are equivalent. So yeah, and you can run it in both directions. So that's the big thing, is to get out the wheel and size difference, you have to be able to run it both directions. So you have one that's all right turns and one that's all left turns. But it really doesn't have to. It doesn't have to be a square. It could, for that matter, it could be a circle. Right. The main thing is you have to go through 360 degrees and get back to wherever you started. So my experience is, yes, that will work fine.
Okay, good to know. So that aspect is sort of same basically.
I'll go one step further. If you could drive the robot remotely, as long as you drove it around a big circle and came back to the starting point, you could also collect the data that way. That is, if you just had joysticks or whatever.
Yeah.
It's really totally arbitrary. The whole trick is to have the robot record where it thinks it is. So, okay.
So the one thing, so I have the book, and I don't remember what maths they were doing in the UNB mark, but what I was thinking of doing then with the data that I can collect is I can retroactively run through all the odometry update steps, right? Sample by sample, right? But with different calibration parameters to see if a different calibration parameter would give me the correct end result. Because I know I'm going to end up at 0, 0, right? So.
Well, I think you can do that, Chris, but it's more complex than you need. All you really need to do is run it several times. The UNB mark says probably a minimum of 5. Each time, just one time around, and record the location at which it ends up.
Okay.
And that may be either way you do it. You put it back at 0, 0, and you record where it thinks it is. You'll then get a spread of numbers. And if, as far as the wheelbase is concerned, if the wheelbase value is wrong, then when you go clockwise around that circle and you go counterclockwise around that circle and you plot those points, they'll be symmetrical. The error will be symmetrical. And you can reduce the wheel size error until they converge at 0. But the wheel size error, not the wheelbase, but the wheel size error, will be asymmetrical, because basically it's causing the robot to turn more tightly in one direction than in the other. And so you can, by plotting those, you can see the asymmetry, and that will suggest which direction you need to move that to adjust it. I've found that you can actually just do this empirically, and the solution converges real quickly.
I see. So, okay. So for a moment, I thought I came up with some novel way of doing odometry calibration, but you're saying in the end, it's not all that different.
Well, I think the idea of having it do a line follow, that part's unique. I know in the original paper, he suggests that you could use sonar to know when you've gotten back to the startup, which was kind of the inspiration for what I did with my RCAT robot.
Right. All right. So let me sort of kick this off here. But if I do present here, and I don't know if this is going to confuse the heck out of things. Oh, because Carl is presenting, so now I can't present, but I wanted to present.
I think Carl just stopped presenting.
Right. It should be all yours. There you go.
All right. I mean, I still have my phone pointed at my robot, but you should. Okay, hang on. Why is it not? So I don't know if you can see. I don't have a way of checking if you can see my terminal window here or not.
No, all we see is the robot, the floor.
I think Carl is still presenting. That's why.
No, you're presenting, and I'm seeing your screen.
That's odd. Wait.
Yeah, I'm seeing your it's pseudo chart -F 60 Python 3.
Okay, that's what you should
Yes,
be
that's
seeing.
fine.
So
Yeah.
different people see different things. It's bizarre.
So I was seeing the car because I had that one pinned, and I unpinned it. And now I see your screen.
Yes, as the audience member, you can pick your own view for this experience here. So like I've set the recording up to the tiled experience, and it shows the Python window that you're presenting, Chris, is the main part of the screen. And on the right-hand side, the presentation shows the photo from the stream from your camera phone.
All right. I had
With Doug
something
P above and John K
pinned,
below.
So that confused me because I had something pinned anyway. All right, so you can.
And speaking as someone from outside of the country, my understanding is that people in the U.S. now get to choose their own reality.
Yeah.
We've done it for 4 years. What do you mean?
I've done it my whole life.
All right. So if I kick this off, and so you can see the robot. So it's gonna do, I don't know, a couple loops around this, and you can look at some of the data. All right, so it's gonna faithfully complete the circle 5 times, and so in my terminal window, I'm not at full speed, but at a much reduced rate. I'm just spitting out, most of the raw data. And what I want to look at in the end is sort of what my IMU is telling me, which is this first number here actually is the angle coming from the Romi's built-in IMU. All right, and so I think you just saw what it did is, when it hit that line here, the 10th time or whatever, 11th time, then I made it slow down, right? And then I hit the brakes when I reach the next line. So basically, again, the idea is I come to a very controlled stop, as centered on the line as possible, right? Because that way, I'm gonna be back exactly where I started. I mean, with very little error, right? That's why it's so important to have this extra line so that I can know when it's time to slow down, right? Now, if you see what I'm spitting out here now in the data, what I wanted to look at is this first number, which I'm happy about, but I wanted to ask a little bit about IMU there to the experts out here, right? So I did 5 loops around this circle, and I'm off by 0.2 degrees, which, frankly, I'm pretty happy with. So my odometry is not looking that great. I gotta tweak that. My X is off by 31 millimeter. My Y by 9 millimeter. My angle by 10 degrees almost, right? That's obviously a problem here. and I'm using the odometry calculated angle, I'm not taking it from the IMU. So I got to clearly calibrate my odometry, which is the whole idea here. But I'm pretty happy with what the Romy's LSM 33 something rather IMU is giving me. And, I'm just, trying to figure out, what I can expect when I run this for more over greater distances, right? Sort of what sort of accuracy over time can I expect, from those, those guys who have used IMUs a lot. I'd like to have some comment there, but also I'm comparing this to the B&O 085, and you can see here on this screen, just before I ran it, I reset the B&O, and so it started out at 0 degrees. So here's my yaw, pitch, and roll. I just care about the yaw, right? 0 degrees. But if I now look at the B&O again, it's off by 10 degrees. Okay. Now, what's interesting with the B&O, and I can go this in both the different directions. If I go the other direction, I will be off again by 10 degrees positive. So it's consistent, which gives me hope, right? Because I'm consistently off by 10 degrees when I run this around the circle here 5 to 6 times. Every single time, the B&O gives me an error of either minus 10 or plus 10 degrees, depending on which direction I ran it in. So clearly there is something going on here that may be just subject to calibration. And I'm using the B&O 85 in the simplest operating mode, and that might be the problem. I'm using it in the robot vacuum cleaner mode, where it literally just spits out the data at 100 hertz, already pre-processed. It just gives you, yaw, pitch, roll, and the other data. And it's supposedly already fully, fused and so pre-calibrated or something. But so I'm not happy with what I'm seeing here, but I got to dig in more and maybe use some of the other operating modes of the B&O 085. But again, the Romy built-in IMU was giving me less than a degree of error, which I'm very happy with.
Chris, is the other one, the B&O problem that you're having, does that one use a mode in which the magnetometers are enabled? Oh yeah.
Back to the other screen now. You asking if the magnetometer is enabled in the B&O? I believe what I read about this robot vacuum cleaner operating mode, what I've read suggested that they are using that magnetometer data, and you guys have pointed out before that that's a problem, right?
Well, half a degree or less than 1 degree of error is excellent. And I'll come back to that. But who's echoing me? But 10 degrees of error is unacceptable. That's way off. So
yeah.
It sounds like the error is accumulating and something's pulling it off. And I just wondered if the magnetic forces might be doing that. The other thing I'd say is, when your robot comes back around and stops on the starting line, as accurate a job as you're doing at line following, you really don't, you can't really guarantee that it is actually 100% normal to that line, the way it was when it started. And I would say that you can't guarantee it better than a degree, and that's what you're getting. So that it may actually be even better than that, is what I'm saying. So I think that's
yeah, I mean, I agree. I mean, I wouldn't, within plus or minus 1 degree, you're right. I probably can't stop more accurately than that. So again, so that Romy IMU is doing reasonably well, but it's obviously just like a 45, 50 second run. I am not really accounting for drift at this point. I'm not measuring drift. I'm just calibrating, or I should say, I'm measuring the offset just before the run. So when I hit start, it's going to sit there for 1 second, right, still, and calculate what the offset is, right, and then use that offset. So that way, every time I run, I'm in a sense, kind of, I don't know, calibration is not the right word here, but I'm measuring again what my static offset is. So that probably helps with the accuracy here.
I
Obviously,
think so.
if I want this for 10 minutes, then that might be a little different.
I think if you've seen me run the RCAT robot, you probably see that I reach down, I hit reset, and then I wait about 6 seconds. And then I say go. That's what's happening in those 6 seconds. Well, having run these things for hours now, my starting point was, well, you know, a 5-minute robot contest would be a real long robot contest. So let's just see if I can't stay stable for 5 minutes. I have the longest periods of the ones I've run it where I still maintain what I would call accuracy have been on the order of 20 minutes. So I think once you get it all dialed in, that's not unrealistic. But as I say, you know, shoot for 3 or 4 or 5 minutes, like a robot contest. And I think that someone had said during the Can-Can contest that they didn't drift at all. That might have been Scott, or maybe it was you, Ray. Somebody had said that's probably a 5-minute contest.
I can answer one thing about the BNO85 from my experience with it is that it's a bit different than the software code, at least in Python for the BNO55, in that when you start it up and configure it, you set up, import and set up specific reports. And so one of the reports, for example, is called BNO Report Accelerometer. And it will throw errors if you ask for data from a report that has not been enabled. So if you don't enable the BNO report magnetometer, it will throw exceptions if you try to get a magnetometer-based reading. So if you're only using the gyroscope, just set up BNO report gyroscope and maybe the accelerometer and nothing else, and you can be pretty assured that the magnetometer is not enabled. And that's probably the only advice I can say, because apart from that, there's like the geomagnetic rotation vector, and there's a bunch of other ones. But if you don't enable them, you can be assured that they're not turned on.
So I've been looking at the BNO55 in the last week. Actually, I've spent some hours with this, and I've been trying to read and understand what's going on, because I don't have anywhere near the time that any of you all do on the device. But it's clear to me that the BNO55 and the BNO85 use the same chips internally, and the difference is the firmware that's loaded in the device. So the BNO55 has one set of firmware to interpret the hardware. The BNO85 has a different set of firmware. It exports different values and it runs differently. And what I can tell you from what I've learned on the BNO55 is that it has the fusion modes and the non-fusion modes. And the interesting thing is that the non-fusion modes seem to spit out raw data. So then you've got to measure your own offsets and keep track of that. The fusion modes have some kind of automatic background calibration that runs all the time that you can't disable. Right. And what I've found in my experiments is that, first of all, the magnetometer, it wants you to help it achieve a calibration after every power up, and that was untenable to me. So I picked one of the 6 or 8 fusion modes. Yeah, I want to just turn it on and have it be pretty calibrated, and then let it calibrate in the background and go. And so I backed off to one mode that in the BNO55 they call IMU Plus, which is a fusion mode that combines accelerometer and gyroscope. And what I found is that with the sample code from the Adafruit library, you can actually do a manual calibration on your device or robot, save it to the Arduino Mega EEPROM, and then since that one only relies on the accelerometer and gyroscope, when you turn it back on again, there's some values you can read to tell you the current status of the internal calibration. And it gives you the calibration of each sensor, accelerometer, magnetometer, gyroscope, and then the calibration level of the fused versions. So I was playing around with a lot of time on moving the device on, can I power it up, get the same values just on power up, turn it off, reboot it without changing power. And it was really interesting to me is that right now I have the mode where Actually, I actually got a pill bottle, and with my standard assembly techniques, I put it on this robot, and there it is, the B&O 55 ready to go. And I have no doubt that if I would power this up right now, it would come up with the accelerometer and the gyroscope fully calibrated, even in the fused mode. But what I found is that if I let it sit and run for a few minutes, actually, for of all things, the accelerometer loses calibration. It just stops being calibrated. The gyroscope stays calibrated the whole time, and the accelerometer goes out of calibration. And that's just sitting still. So I haven't figured out what's going on there, but I suspect that the B&O 85 firmware might be doing something similar. And if you look, you might be able to find some kind of background auto calibration task and monitor its understand its assessment of how accurate the calibration is. Because the one caveat I'll give is that another thing I did was to try and compare the magnetometer just sitting around here in my parents' house to some other devices. And so I used when I move it sideways, it turns off. But I used the compass on my watch and the compass on my phone because they're using the same chipsets, right? And I found that they were remarkably accurate. And you never have to do anything special to calibrate these. They just take care of themselves somehow magically. Now they're moving around, giving some noise to the system, but it seems like these require so much less effort to get decent results from than when we try and do them raw in the robot. It's just driving me nuts because it seems like we ought to be able to get similar results because we're using the same chipset.
Carl, I think you found that if you were to take your iPhone and turn it off, like power it down, and then turn it on from scratch, you wouldn't calibrate until you started moving it around. That the watch and the phone do require, and in fact, part of the reason why the B&O 55 is calibrated by doing this figure 8 is because that's actually what normally people would do just by randomly moving around, which is what calibrates those magnetometers. And the only thing I can add, though, is that while you're right about the hardware of the 085 and the 55 being the same, the software, at least in the Python implementation, is remarkably different. The 55 is very mysterious. The 85 is not mysterious at all. It's pretty straightforward. It doesn't have any fusion modes. Behind the scenes, it might, and that Hillcrest library seems to add some stability. But that whole way of setting it up with reports is very different than the 55. And so I think that Chris's experience with the 85 is kind of similar to mine in that I've seen those kinds of results. Whereas with the 55, which I really like when it works, it is so mysterious that I've kind of given up on it.
Yeah, I mean, like I said, I've put it in the simplest operating mode. So I probably shouldn't expect more, but it's you set certain pins, the actual hardware pins, you provide certain values to it, and when it powers up in that mode and then starts spitting out data. So it's very easy to interface with it that way. But so I'm probably not getting the full value out of it, right? I haven't used yet the actual libraries because they don't fit on the Qt Py. So I got to do that differently. But that's what I'll try next. I'll try one of the other report modes, and that, especially one that doesn't include the magnetometer info. And I know there are some modes where they don't include that data.
Well, Chris, as apart from the 055, there's no modes as such in the 85, and that it's simply an accumulation of reports that you import and then configure. And so it doesn't have like a fusion mode, as far as I can tell. Maybe some of the actual reports under the scenes or behind the scenes are actually using fusion. But like I said, if you don't activate a report, you can't get data from that particular part of the device. And so if you only activate the accelerometer and gyroscope reports, there won't be a magnetometer at all, as far as I understand.
I see.
The fact that it's not reporting a magnetometer has got nothing to do with whether it's using some kind of fusion internally. I can't imagine it's not using fusion.
Really?
No, it is. I mean, definitely.
It has to be. And you have to be able to control whether or not you want magnetometers internally to contribute to that solution.
Yeah, that's my understanding as well.
Don't want it to. Yeah. I don't have experience with the 85, but 55 has been pretty rock solid for us whenever we do it without magnetometers and make sure we're controlling the heat on the device.
Same here.
Well, the only thing I can say about the 85 then is that if that doesn't seem to be, apart from the way you configure the reports, from my experience with the Python library at least, is there doesn't seem to be a configurable way to set up the various parts of the device then, if you're not, because it seems to be all about whether or not you turn on certain reports. Unless everything is always on all the time, I don't know.
No, I think the different reports, and I don't know if I'm using the right terminology, but from what I've read, which isn't much, I have to admit, for different use cases, right? In some of the very high-level documentation, they describe these different use cases, like, you know, virtual reality goggles and all kinds of gaming scenarios. They fuse the data differently internally, because sometimes you want data that's smoother, sometimes you want faster update rates. I mean, so they do it. They fuse it differently internally, depending on what you're asking it to do. Now,
Right.
how you ask it to do what, I don't know yet, but that's I need to try that out. I was hoping that it would be significantly better than just its simple gyro that's on the Romy, but you know, I mean, maybe that's not true, but that's what I was hoping, right? I bought this $20 device from Adafruit. I was hoping it just spits out magic number, you know, the right number at all time, but
No. The only thing I can say is that, like I said, these are called reports, like B&O report accelerometer, but the way in the code that you turn it on is enable feature. That's actually, I'm looking at the code. It says enable feature, and you would say enable feature B&O report accelerometer. I'm assuming if you don't enable any features, it's not going to turn on everything. So, I mean, maybe we need to dig around on this a bit, but my impression was if you didn't turn on the magnetometer or any of the features like the geomagnetic rotation vector report, you're not asking for a magnetometer if you only ask for the gyroscope. Wouldn't that make sense? Like, you're not asking for anything that requires a magnetometer. Why would just turning on the gyroscope turn on the magnetometer?
well,
in a way,
some of the
it
reports
makes
give you
sense
the
for-
actual orientation, right? So you might be right when you're asking it just for the raw gyroscope data. That's probably that's what you're gonna get. But like in the mode I'm in right now, it spits out your pitch and roll, right? It's not spitting out raw gyroscope data. It's giving me an angle between minus 180 and plus 180. That's the number it's giving me. So a lot has gone into the calculation of that angle. And I think the same is true in some of these other report types where it's giving you an absolute heading, right? Which it has calculated using all this other information. And that's to me the added value, right? If I just wanted a gyro, well, I have a gyro that gives me raw gyro data. I have that. What I purchased, right, is a device that does internally some sensor fusion and gives me an absolute heading, because that's the information I'm after, right? I just want the heading. I don't care about raw gyro data. I just want to know which way I'm headed. I'm not in an absolute global sense, just relative, right? Start out at 0, end back at 0. That's what I want. I was hoping that device would give it to me, but you know, clearly it's a complex device with different ways of setting it up. So, you know, need to dig into that some more.
Well, Chris, both of you and I have kind of the same goal there, is that ultimately I'd love to get an absolute value, but absent that indoors, I'd be happy to get a heading.
No, I don't care about true north. I just call it 0 degrees when I'm starting, right? I just want it to tell me, all right, you're at 0 degrees now, you made a turn, now you're at 90 degrees. I don't care where north is. I just want, so I shouldn't call it an absolute value, but I just want, you know, a heading information in degrees, you know, that is stable over time.
Well, I think we're agreeing. That's we call that a relative heading, and I just want a relative heading at the outset. And if I can get absolute, great. If I can't, the relative heading, I'll work with that.
And that's what the BNO 55 does in this IMU plus mode. It's a fused mode, but it ignores the magnetometer. And what it does is when you power it on, it takes a 0, it outputs a 0 heading as wherever 0 was when you first powered it on. And until you power it off, that's 0. So then you could line it up on your course and then have north on the course be north, or you could have it lined up to true north and that be north. But that's the mode I was trying to use. It was just shocking that it lost the accelerometer. And another thought is that it'd be interesting on the firmware for the 085 version. What I learned on the 055 version is that there's, or maybe no, this isn't the raw Bosch data sheet for the 055. They talk about setting these different modes and choosing them wisely because it can severely affect battery usage. So if you have a wristwatch, right, or a phone, you're going to really care about battery usage where we don't on the robots. But I suspect that that could be a correlation then that like in your 85, if you select a report where you only want some values, unless it needs the other sensors to calibrate the data, it ought to turn them off to save battery. I mean,
so definitely more reading to be done there.
Yeah.
I wanted to make two more points on what I was doing here with my line following and data collection setup. I think you can still see my screen, right? Yep. So this is what the data looks like that I'm collecting right now, and I kind of it's spitting out a comma separated value file, so I can just open it up directly in Excel. It's kind of my favorite data analysis tool, and so obviously that then allows me to do things like, okay, let me look at my odometry data, and you can see that I don't have a column header. I kind of prefix certain columns with a label, and I do that in every row, just because I find it easier to process the data that way. And when I'm looking at it, when I'm looking at row number 5000, I see, oh yeah, okay, these two numbers are raw encoded data, and after the O comes my odometry data. So that's why there's these columns with just a letter in it. But spitting out the data in CSV format makes it convenient to sort of just open it up in Excel, right? And then I've just highlighted the X and Y odometry, the calculated X and Y, and you can do nifty things in Excel, obviously, right? So you can see me going around in my oval here 5 times, and you can see sort of how my angle drifts over time, right? So just being able to see some of this, already obviously know that I'm off by the time I get back to the starting point, but sometimes just visualizing the information, right, just kind of helps you understand what's going on, or helps you spot additional issues, right, that may not be immediately apparent, right? I mean, in this particular case, I'm not spotting any issue that I didn't already see by looking at the last data point, but sometimes you see other weird noise, happening that you wouldn't see by just looking at raw numbers, right? So that's why I like this in Excel.
One thing you can see in that, Chris, if you bring that plot back up, you can see that it's very symmetrical and that the error seems to be spreading at a constant rate through time. There are no sudden jags or anything. Each offset is about the same as the previous one. So that makes it look like there's some regular systemic error. Most likely your wheelbase needs to be tweaked a little tiny bit.
Yeah.
Time goes back up, but I would look at that and I would say, well done. There's no noise in it. There's no erratic wiggling back and forth to stay on the line or anything. So that looks great.
Yeah, so that's that's exactly the idea of collecting the data and looking at it and making sure I'm not missing something. And I plan on doing the same with the LiDAR data. And now the second point I wanted to make. So I'm doing this in Python, and so Murray will appreciate this, right? I mean, we've talked about his pain points with Python and threading, and my challenge here doing this in Python, A, because I just wanted to do stuff in Python because I should learn it, and B, because some of the libraries happen to be in Python. My challenge was, I have to sample this IMU at 400 hertz. And yeah, well, I had it initially at 800 hertz, but then I took it down to 400 because I can't keep up with 800, not in Python. So one question: is it necessary to sample the IMU at that rate, right? Or I mean, at what rate should I be sampling the IMU? I mean, I'm telling it to produce data at 400 hertz, so I gotta read the data at that rate. But you can tell that IMU that's on the ROMI to work at 100 hertz, 200 hertz, 400 hertz, and so on. And what is it? Will it give me better, more accurate heading if I crank up the rate? Who can comment on that? Go ahead.
The answer is yes.
I don't believe it gives you a more accurate heading.
Depends on
Doug,
whether you...
is Doug Parody here? Yes. Doug has observed in his own work with gyroscopes especially that because they're so noisy that you really have to sample them at a really high rate, but then you're filtering them back down to a low rate. So if your IMU is already doing that for you, just ask for the data at a lower rate. If it's not, then you might want to sample at a higher rate and do your own, running average or whatever to clean that up a little bit. Doug, am I misquoting you?
I think if you're right, if it's got a Kalman, the sample rate should be high. All right. The question is who's doing the sampling. All right. If you're doing it with like a BNO's 055, it's going really fast inside, and it's going through a filter, and you were asking for it. You can ask for it at a lower rate. You know what I'm saying? But that, inside it's going as fast as it can. If you're taking raw data, I'm lazy, so I never take raw data. I always take the filtered data from, when I've had a chance to buy a BNO 055, I just said, this is what I want. And that's the reason why, so I don't screw around with the raw gyro numbers. Now, the thought would be is that you should be, and I think especially the accelerometer should be doing it really fast, and the gyro as fast as you can. Now, I don't know, I'm looking at his 0.01 degree.
Yeah.
Whatever you're doing, it sounds like it's doing it right. And I agree with Dave in that, it doesn't seem like you have anything odd about your data.
Yeah.
It's not like flipping back and overlapping and stuff. It's like, zoop, zoop.
No, that was odometry, right? That was the odometry and the angle coming strictly from odometry. The gyro is not, it wouldn't be, if I override the angle that my odometry calculates with the angle that I get from the gyro, this wouldn't look that way. But, I gotta, I guess, read the data sheet and maybe Ray, that for the IMU that's on the ROMI, I don't know how much work they do internally and the data it spits out, whether that has already gone through some filtering. I honestly don't know. So I kind of just assumed that I had to sample it as fast as I could externally.
So here's just jumping in. Here's something to look for in those other IMUs. This is the Bosch data sheet for the 055, and they have a table like this for each of the 3 different sensors, and you'll see the accelerometer in the non-fused modes. You can specifically change the range of measurement, the bandwidth, and the operating mode. But in the fusion modes, it just automatically takes care of that for you. So you can get a pretty wide range of bandwidths on here. Look at that, from 7 hertz to 1,000. So, you really it's nice to have that off the shelf, just plug it in, you get something sensor, right? But it also really helps to know what's actually happening under the covers, because it could vary dramatically.
If it gives you the right answer.
That's what matters.
Yeah, so you know what, I should just cut the rate in half and see how well it does. I could just try it, because what happened, and that was my last point I'm going to make, doing all this in Python, reading the IMU at 400 hertz, and then also interacting with the ROMI hardware, which I'm doing at 100 hertz. in Python, which can't really do multi-threaded properly, I was running out of time, basically, right? I mean, that's, you know, unfortunately, that's the challenge you run into when you use these sophisticated means to do very simple tasks. You know, the sophistication gets in the way of doing all the simple stuff. So I was almost running out of time, and I've kept track of how much time elapsed since my last IMU sampling. I'm keeping track, well, because I should be doing it every 2.5 milliseconds. Otherwise, I'm falling behind, right? I'm gonna miss updates. So I keep track, and it's you know, every 10 seconds or so, I guess I miss one sample, something along those lines. So not too bad, but I'm on the hairy edge. I mean, if I don't run this at super high priority, you know, then basically all bets are off. I can't keep up, because the problem is interacting with the Romy controller. That itself takes about 2 milliseconds, right? So every time I interact with the Romy controller, 2 milliseconds have passed. I better go read that gyro quick, otherwise I'm gonna miss the sample, right? So I'm barely able to do it in Python, and you know, it's a bit frustrating. And the other one interesting thing I found, I mean, for those of you using Raspberry Pis, so on the Raspbian 32-bit, on the Pi 4, that's where these results are from. It works. I don't have a lot of headroom left. You know, I'm almost running out of time here. The same software running on the same Pi, but running on a 64-bit Ubuntu, not happening. I constantly miss my deadlines. I shouldn't say constantly. Every time I get the data from the Romy, which again takes about 2 milliseconds, probably a little more on the Ubuntu. Doing that at 100 hertz means 100 times a second. I'm sampling my IMU too late. So, you know, I had a feeling that Raspbian is just a lot more optimized than Ubuntu, which I'm still a bit undecided on what to run on my Raspberry Pi. There are benefits to running Ubuntu when it comes to RAWs and whatnot, but the Raspbian is it just seems a bit more optimized, and this is what this has shown. I mean, it used the same code, actually used 50% more CPU time on 64-bit Ubuntu, and I don't care about the CPU time, right? Whether it's using 10% of a single core or 15% of a single core is irrelevant. But there's a correlation between that extra CPU time and not meeting my timing requirements in reading the IMU data. So the bottom line is Ubuntu is a little slower. And I don't know if it's Ubuntu or the fact that it was 64-bit. And bottom line is, you know, Python is just slow. So when you're doing trivial stuff like that, meaning reading something from I2C at a, you know, at a good pace of a couple hundred hertz, it's just hard to do that in Python. Is what I learned with this exercise.
That's why I would think that this would be another thing that I'd be doing on a, you know, something like an ARM chip, and I wouldn't be doing this on a Raspberry. What I'd be doing is sending the information, the calculated information to the Raspberry if that's what you need. But trying to run the IMU on the Raspberry Pi, I don't really see the advantage of that.
I have to, you know, I have a little bit of code doing I2C transactions in C, and I don't have any data to kind of compare performance, but I'm close. Because again, I think it's mostly Python that's slowing simple stuff down to a point where, yeah, it's just no longer that practical to do that kind of stuff. But I bet you in just straight C or C++, doing some I2C transaction, I can do these 400 transactions a second, you know, without that many issues.
Chris, does the I2C interface that you're using, does it generate an interrupt when it gets a complete packet?
It must, but honestly, I don't know, right? Because when you're working on Linux and something like a Pi, you so many layers removed from the hardware that I honestly don't know how they have implemented the device driver on Linux on the Pi to use the Pi's, you know, I2C hardware peripheral. I don't know how they've implemented it. Somewhere down in the weeds of the Linux kernel driver for I2C, there usually are interrupts going on, but I haven't looked at it. I would hope that they're taking full advantage of what the hardware that's on the Pi can do. I would hope that they've, taken care, advantage of all the hardware capabilities.
Actually, David and I have been discussing similar things in the last week, and I've been using the PyO or whatever it's called library as opposed to the RPI GPIO library. And I had never dug in to find out what was actually happening. But when I did, it turns out that the PyO library, or however you say that, is actually polling. It's not using interrupts at all. It's polling at 5 microseconds, which is plenty fast for most things. Not at maybe 500, 400 hertz or something like that. But my robot runs at 20 hertz. But 5 microseconds seems to be the polling rate. It's not using interrupts at all. The RPI GPIO library does have late support within the last year or so for interrupts, and I thought about using that. Right now, I'm sticking with my PyO library because it's fine for what I'm doing. And I will say one thing to defend the Raspberry Pi, because I know that Doug and I have gone on, he doesn't like Raspberry Pis and Python very much.
No, I think they have their place.
Well, but not the place where I'm using them, apparently.
Right, I mean, I don't think that's a basic robot controller. We're close to the
but I will defend that.
That's not where it should be. But if you were doing, if you're doing AI, or if you're doing OpenCV or something along those lines, that's where you should be. So you could argue you might want to start doing it in C instead of Python, but Python's going to be the way to learn.
Well, I've been using Python for the last year and a half or so. I'm using it on a Raspberry Pi 3 B+, which isn't the fastest Raspberry Pi. All of my sensors, with a few exceptions, including my motor controllers and everything, are on I2C. So I'm using about 15 I2C devices on a single bus on a Raspberry Pi. And I have been able to run the robot around with PID controllers smoothly and using sensors without any real problems. I have other problems.
Works for you.
Yeah, I know. And in fact, I'll later talk about what I've been dealing with on a new robot. But I will say that given that I've got like somewhere between 12 and 15 or 16 I2C devices sometimes running, I'm not running out of space. I'm running a 20 hertz loop and things seem to be fine. I'm not seeing the robot getting into some cycle where it can't handle data. Now Chris is trying to run things a lot faster than I am. So
I'm not running everything that fast, right? Again, keep in mind, I have to sample. Well, I've told my IMU to produce data at 400 hertz, so I better go sample it. And like maybe I don't need to go that fast, so I need to look into that. But the rest of the logic runs much slower. But at that low-level stuff, I probably shouldn't be doing it in Python. I still think it can be done on the Raspberry Pi. 400 hertz is really, the Raspberry Pi won't break a sweat, and if you do it right, you can meet all the timing requirements. But in Python, it's just not the right environment to do something at 400, 500 hertz predictably without missing a beat. So that's what I learned. Python is slow. I've tried PyPy, which has a just-in-time compiler, made things slower. I tried some other compiler that compiled it to C code, made it slower. So whatever, people have supposedly solutions for making it faster, but the bottom line is, Python is not as fast as what some of us are used to, right? And doing things in just C and C++.
I think, and part of the reason I'm using a Pi and Python is I wanted to learn Python, and my way of working is that I SSH into my robot and do all the programming on the robot. And that's a really nice way to work for me. I don't like having to plug to an Arduino ID with a USB port and all that. I just SSH in. So those two things, and this is, like I said, what David and I have been discussing, are part of the reason why I'm using Python. And I actually really like it as a language. But I don't disagree with David's basic premise. Yes, of course. On a on a STEM board or on a board optimized for that. In any case, actually, I suppose, are you, oh, anyway, that's it.
I want to hear Donna.
Oh, yeah, I was just going to say, I was going to chime in one thing too on what Chris has been talking about. You know, it seems to me that the quandaries in utilizing the IMU with your design and what all that you're trying to do with the robot, it seems to me that this is a great example of where a distributed computer system would warrant itself well. What I mean is that you've got a dedicated controller board, whether it be Raspberry Pi or whatever, that is dealing exclusively with the IMU, since that's so it's so CPU bound, and there's so much computation there, and you need to have that high rate of sampling so that you're not missing your data. It seems to me that that would be a great part right there of your distributed system. And then you've got your main board, whatever controller board that you want to use for that, that is for your logic on for your robot. And then you've got your communication methods or mechanism, whether it be I2C or serial or CAN, whatever you're going to do there to make everything work together. But it seems to me that, I mean, I don't have any direct experience at this point in my robotics development experience directly with doing a lot of distributed systems. But everything that I've read as far as computationally intensive sensors or application, whether it be something that's AI related or especially vision, or a lot of our CPU intensive sensors like IMUs, etc., that the idea about using a distributed system is going to be your best route. So that's my take on that.
Yeah, I think the world will eventually be just all smart sensors, and they'll just connect up to a bus. Hey, wait a minute, that's what a car is. You know what I mean? Think about it. That's how they do it in a car. And, even the little things like a push button has a CAN transceiver on it. You know what I mean? You would think, oh, well, you just push the button and it just closes the circuit. Nah, that's not what's going on. It's feeding, somebody's pushed this button onto the CAN bus, and then the microprocessor is deciding, well, somebody pushed the button, it's time to do this. So I think that's what you're saying, Donna, if I'm not trying to put words in your mouth, but I really think that's the way eventually we'll go. And I've definitely found from my own experience is that when I can get a solution for a part of the problem that works, and I don't have to mess with it anymore, and I can move to something else, and then I can just plug that. And if it's got an Arduino on it or something else on it, I don't care. I just plug it in and have it talk to this other guy and tell him what he needs to know. Now, and I think that's the whole idea behind ROS. If you really look at the original, the idea of ROS from the beginning, it was just simply a communication protocol. I think what do you want to do with it? I think if we were really advanced, we'd be using CAN bus, but a lot of the stuff that we work with doesn't come built for CAN. That's why we don't. That's why we use I2C, and that's why we use serial ports and stuff like that. It's because we don't, if we aren't using ARM chips, you pretty much don't have CAN. Yeah.
I'd like to offer a slight devil's advocate to that position.
Go for it.
Given, I'll start with the observation that all my robots actually do have multiple processors that talk to each other. So the camera has its own processor, the GPS has its own processor, the IMU has its own processor, and so forth. So, but with that caveat, when you start breaking out sensors to individual processors, you've introduced a whole new set of problems. The first set is the comm link between the main computer and the processors can become a bottleneck. Secondly, you have to define what the communication is going to be between those two. And as you work on your robot, you may find that that needs to change. And now you actually have to have two development environments, one for the main processor and one for this other processor out there. And when you're working to solve a particular problem, you have to make the determination about which end that problem should be solved on. And should it be solved on the remote end? So you're opening a big can of worms when you start spreading things out across multiple processors. I say that with the caveat that that's what I'm doing, but in my experience, it makes things more complex, not easier. If talking to a particular device means talking across some kind of software protocol to another computer versus talking to that device means toggling a couple of GPIO pins. The toggling the GPIO pins is always easy.
I would tend to agree with that really strongly in that one of the things that I did, I guess about 6-9 months ago, is I took my entire front of my robot and made it into one sensor, and it uses one of these little IO expanders that has a Nuvoton MS51 8051 compatible processor on it, and that's got 6 PMW or digital pins and 8 analog pins on there. And as David said, now I just need to go I²C. But the problem with that is that if I had, as I used to, connected all of my analog infrareds and my bumpers directly to the Pi, I need to pull those. And this is a little bit slower, but not really. It's kind of a toss-up. It was about 170 milliseconds for me to go through the whole round of grabbing the information off the GPIO pins from the Pi. This one here, it's about 85 milliseconds to do the same thing. So I actually gained a bit. And the nice thing is that I can take my entire front bumper with all 5 infrareds and the 3 switches off the front of my robot, and I just mounted it onto a different robot now. And the only connection is 2 bolts and the I²C connector. So as Doug said, it's like that's kind of where I think we're heading, is these little tiny chips are becoming our subprocessors. And I held this up because this is a little I²C RGB potentiometer, and it uses the same MS51 processor. So rather than plugging a potentiometer, which I've actually also done into my robot, I can also just use this, and it's got a library to control it. It's got a little RGB LED in it and everything. But the point is that here's another, just like you said on the CAN bus on a car, I've got just a potentiometer here, but it's not. It's a whole processor. And I do agree that's kind of the way it's going. And I went ahead and bought one of these things, which is the MS51 board with the link board and the MS51. And this is the development board for playing around with one of these. And it's a whole different world. I'm going to be in assembly well, I can get it in C, I think, but I think it'll be an assembly, MS or 8051 assembly, the same language we used in the 1980s. And there's a little, unfortunately, Windows-only IDE for it. But if I really want to go down that route, I can do what the engineers at Ada or at Pimoroni did and build a little MS51 onto a board, or do something like this, or learn to program this one. But it is a whole different world than doing it in Python on Pi. I've got now 2 development environments, as David said. But I totally agree that that's where we need to go, or that's where we're going anyways, that you can't do it all in one processor. I think Don is right. You need to create sub-processors.
I'll take that bet.
And I opened my mouth, so I can tell you what I've been doing. I've got a new robot. I took the front bumper, the integrated front sensor off my earlier robot, and I took the drivetrain off that robot. I didn't have to dismantle it. I just built another one. And I built a differential robot. And I just posted a link to the blog post, which is a work in progress. It's called the KD01, but it's kind of the same thing as my existing robot, but differential drive. And David's been very generous in helping me get through some bugs. Turns out that I never thought about just hand rotating the wheels, but it turns out that on the new robot, when I rotate the port wheel counterclockwise, I don't get the number of step counts off my encoders that I've been getting on everything else, which is usually 494 steps per rotation. I get like 340. And I've been on the oscilloscope. I won't bore you guys, but I've got the oscilloscope here. It's up and running. I've been running the thing and everything works fine, except that the step count is backwards. And I was looking at the oscilloscope. I thought there'd be something on that. I'm getting an A and a B square wave. And the only thing, and the reason I'm kind of going into this in any detail, is the only thing I can see that's different between that and the other ones is that the A and B waves aren't as far apart, that the A and B are very close to each other on the rise. And
Yeah,
I'm seeing
that's what I was gonna say. You're missing what they have to be to really be right. They need to be 90 degrees. Okay. And if they're not 90 degrees, not only are you going to see different counts, but you're going to see when you use different speeds, you're going to get different counts.
Yeah.
Okay. And so if you're lucky, your Hall sensors are on long leads, you know, and just leaning against the magnet.
Mm-hmm.
And that way you can adjust it a little bit. Okay. If you're unlucky, you know, they put it right next to the PCB and there's nothing you can do with it.
Well,
if you're, you know, if you're really lucky, if you're looking for another motor, is like on the Pololu, it's the two sensors are actually integrated into one sensor and they're matched with the wheel.
Right.
And you won't have a problem.
I'm using the OSEP encoders, which come as a separate unit and actually have to be mounted on the beam that holds the motor. So it's very much a manual alignment. And the only thing I found is that the two little tiny 3-pin Hall connectors, which are like, you know, 2 or 3 millimeters square, is that you can very delicately bend them just slightly, and you can also move things around. And I've tried doing that. But what the tricky thing is that clockwise, it's fine. It's only counterclockwise that it's off. And so
something
sounds weird.
I have a question about encoders. I got a question about encoders.
You know I'm sorry.
I got a question about encoders. I was watching Bruton. You guys know that fellow on YouTube that does all the kind of crazy robots and all that kind of stuff. You know what I'm talking about? Anybody? I'll find a link. But it's a cat named Bruton. He builds a lot of different robots, and he had a different encoder that I've ever seen. On the back of his wheel, he had a single magnet, and then he had another. And what he had a board with a sensor IC on it mounted right up close to it. I'm guessing as it rotates through, it can check something as it goes, but he says he gets A/B signals out of it, and that's what his encoders are.
Well, Harold, that's what I've got. I've got a single magnet that has 11 poles on it or something like that. It's a single magnet that rotates around past two little tiny, like 3 millimeter, 2 to 3 millimeter.
It's not going past it. I mean, this is a flat IC sensor that's on it that goes to it. I've never seen anything like it. I could have misseen it. I mean, my eyes are getting old. I might have not seen what I thought I saw. But
these use just a single magnet, and it actually, I forget which company it's from, but there's the little magnet that you just stick on the back of the shaft, and it only has, you know, one north and south pole, and it can actually sense the variation of the magnetic field as it rotates around.
That looks like the magnet he was using.
Very small.
It had a little daughter board.
What's
Mary,
that?
I'd like to back up a step. The reason that you have two signals that, as Doug says, need to be 90 degrees out of phase is in order to read the direction. The quadrature encoder allows you to tell which direction the motor is going. Right. But you don't have to read the direction.
You can make a tachometer.
One good test would be to just look for the rising edges on one channel and see if you can get that to be the same between the two sides. Don't let the quadratureness of it throw you off.
Right.
And then the second thing is, as Doug pointed out, if you're going to use the quadrature, they really do have to be 90 degrees out of phase with each other. One way you can visualize that is that obviously the spacing needs to be the same whether you're going forward or backward. And if they're not 90 degrees out of phase, it's further going one direction than the other.
Yeah, and just to be clear with Harold, there is just one little disc rotor, just as on the little Mach metal gear motors. These are just a little bit bigger magnet, but it's a little disc. And
yeah, no, I understood that part. I just didn't understand that literally, just like Ray just showed, it's just a single magnet with a north and south pole, and there's a flat IC that goes up close to it, and it detects that somehow. And I didn't know if anybody knew how that worked.
Well, that's just a Hall effect. It's just a Hall effect sensor.
Harold, that's got a 12-bit encoder on that chip, so it'll give you typically 10 or 12 bits of data for position.
Yeah, they're fairly sophisticated. Somehow there's actually multiple Hall effects on it, I think. It's made by AMS, and I ordered some, and they seemed like they were taking forever to get here, and then so they actually resent them, so I got 4 for the price of 2. But obviously haven't used them yet. They're still in the bag. So, but yeah, you can get, like you said, you know,
I just didn't think that, and it made no sense to me. But I mean, if this guy's using it, he's built way more stuff than I ever have. So if he's using it, I guess they work. So, and
they work over I2C or SPI.
Say that again.
They work over I2C or SPI communication.
Right. Yeah, and there's a little printed circuit board in here that you basically stick over the magnet.
Yeah. So the centering is quite important on those typically when you center that magnet.
Right. I would assume so.
And it'll give you like a count of 4095 in one rotation, let's say.
Yeah, you can set it that high. I think it comes up with a default of, I want to say 127 or 128 counts, something like that.
It depends on the model. There's several different models.
Right.
Some of them operate much faster than other ones.
Yep.
Yeah.
So the one I've got. Go ahead, Kurt.
If you ever use a Dynametrics servo, or Dynamixel servo, they can rotate continuously, or they can rotate to a position and go back. They're using something like that inside of them.
I got you, because this guy's built balance spots, all kinds of other where wheel rotation and direction are important, and speed, right? He's even got a robo dog, 4-legged dog that looks like it has suspension, but it doesn't. It's watching backlash coming off his encoders to do active balancing and things. So I guess they're pretty accurate on that thing, you know, to be able to do all that. I would assume so.
Yeah, to get 4,096 counts out for revolution, that's
yeah, that's pretty good, right?
To give you put that into perspective, because I was just working on one of my robots. It's got 3,840 pulses per, or I should say edges per revolution. Okay, and I'm using on there 80mm wheels. Okay, so 80mm wheels. So that means one tick is 2.5 mils of a wheel rotation. So, okay, for Murray, I don't know what that is. That's really small.
Yeah.
But that's only at 3840. So imagine what it is at 40,000.
Yeah.
I mean, it's like, you know.
Is yours a Hall effect or an optical?
Mine's a Hall effect. Mine is this is just a standard, you know, inexpensive DF robot motor.
Well, like I said, I'm just using the OSEP ones, and I get I can set it for rising, falling, or both, and I've been setting it for both.
Yeah.
And so I'm getting both the rising and the falling edges counted, and I've just got a simple Python program that has callbacks for each of those, and I could basically double my number, but 494 for a
of open non-conversion.
Pardon?
Are you using interrupt?
No, well, that's what I was saying, John, earlier, that I thought I might be using interrupts because I was just using the callbacks coming off the GPIO library. But when David and I were investigating that, so I dug into the code and looked, and it turns out that what I thought was an interrupt is not actually, that the GPIO library is actually using a 5 microsecond poll. So it's actually polling on the.
Oh, I see. Yeah,
It looks like an interrupt code-wise, but
it might be enough to catch that narrow
oh,
gap.
it's 5 microseconds is plenty. Yeah, it's not a problem.
Oh, I see.
Not the rate I'm hitting it.
I mean, when my motor rotates at full speed, that width of the pulse is maybe about 100 microseconds. So I'm thinking if it's interrupt, and if one edge triggers, there's plenty of time to catch the read the other edge, like read the other line. So yeah, I'm thinking maybe interrupt will help if you use it.
Well, I've thought about that, and I've actually kind of started playing. David dissuaded me from making too many big changes at once, and I'm kind of trying to see if I can get the existing library to work, because I don't think that's the problem. We've actually narrowed it down to being an actual hardware problem with the encoder. I've got 2 robots. The other robot doesn't have any problems at all in terms of, like I said, I hadn't thought about just hand rotating, but I rotated both of the wheels on the other robot 10 times and got almost exactly 494 steps per rotation. So I was pretty close on that. And then on this one, on the new robot, 494, 494, 494, and 360. It's only counterclockwise on one wheel. So it's hardware. It's totally the encoder, something about that encoder installation hardware. So I'm either I've actually put in an order for another pair of encoders, and I'll just swap out the encoder and see if that makes a difference, rather than spending lots and lots of time trying to debug, which is what is probably a hardware problem.
Sounds like from your description, if the phases of the signals are not actually quadrature, then when you're going in one direction, you get an interrupt on a rising edge, and you test the second channel to see which direction you're going. But when you go the other direction, that pulse is moved over, and so sometimes you might miss it, in which case it would say, oh, we're going backwards. So it would subtract the count.
Yeah.
And that might drive one of your, maybe just if you can just orient the sensor in such a way that you get those more in exact quadrature, that problem might magically solve itself.
Yeah, I think you're right, because like I said, until I stuck the O-scope on it and looked at it, it seemed fine. In fact, when I first looked at it, I didn't really get that there was something wrong, and then I realized that the rising and falling edges were almost overlapping at times. So I think you're right. It has entirely to do with something about the alignment of, and maybe just wiggling or moving the encoder around, because it is actually mounted separate from the motor. I'll play around with the mount of it, but I've actually got 2 encoders coming in the mail. They'll be here in 6 months in New Zealand,
So all that digging around in the software was chasing the wrong problem.
Probably, but I did learn something. And actually, the whole idea that you said, earlier, which you've said before, other people have as well, which is that, we don't have to have quadrature encoders. I know what direction the motors are going. I mean, I'm setting the direction. And so I could just basically ignore one of the A or the B and just get counts, because that's all I really need. But the fact of the matter is that
there is an you can read the transitions on both channels, so you basically double the pulses. So you increase your resolution of your encoder by 2.
Yeah.
So that's one of the things you get for using a quadrature encoder.
And you can also trigger on the falling edge as well as the rising edge, so that gives you 4 times the number of counts.
Exactly.
I was hoping Dave Ackley would be here, because before, when we talked about how complicated it was to decode which direction you're going, Dave jumped in and said, no, you're all wrong. You can do it all with an XOR. Does anybody here remember that?
Oh, yeah.
I do. I'm using that.
You're doing that. All right. Sean is our expert tonight.
I'll show you guys when I show you my code.
David, you had stepped away for a moment, but actually I am running on rising and falling, and I always have been. I don't use just rising or falling. I'm doing both. So I'm getting the max count off the encoders as it is.
Yeah.
And that's what for one revolution?
494 steps per revolution of the wheel.
And when you run the motor at full speed and you sample the encoder at 20 hertz, what is your maximum number of counts?
It doesn't. I don't know what. I don't understand the question. It doesn't change depending on the speed of the.
Yeah,
I'm not asking for the number of counts per rotation. I'm asking for the number of counts per 20th of a second at full speed.
Oh, I don't know. I never. Let's see.
That's a handy number to have. Just run the thing max out, and you probably get the same velocity from both motors, since one will probably run a little faster than the other.
David, what's a good number? Because on my Mechanic wheel robot, it's about 130 per sample period, max speed.
No, that's pretty
Well, I like to be able to go 1/10 of max speed, so that would be just 13 samples, which is really kind of marginal for doing good PID.
Okay. Thanks.
I'd also say it's not always so easy to give up quadrature. You know, it depends on the circumstances. So we can tell our robot to go in one direction, but if there's a heavier robot pushing us backwards, you know.
You're saying real world measurements are more valuable than our guesses?
Go figure.
Not non-battle bot conditions, I guess. Yeah.
Well, I'll sign off in terms of my information for the week. Like I said, I posted a link to the new robot on my blog. But just to everyone, thanks very much for all the advice, because particularly David, but everybody, I've kind of learned a lot in the last week, and I've realized, as I've said to David, getting away from LIDARs and all the complicated fancy stuff and just getting the robot to run in a straight line and being able to control it and get good odometry, maybe that's a first step,
By the way, I put in the chat, I put a link to the video where I saw that at, and it starts just a few seconds before they show that encoder and what Bruton's going to do with it and how he puts it in. So it might be of interest.
Murray, I've probably mentioned this before, but in the long ago time, we used to have a contest that was basically for beginning robot builders, and what you had to do is bring your robot in and set it down on the floor and turn it on and have it drive off in a straight line. And if you are so far along the process if you can do that. You have a platform, you can download software to it. Anybody deserves a gold star if they can turn their robot on and have it drive away in a straight line. That's worthy.
Well, actually, David has been sharing some small videos he's made on the floor of his office I had mounted that challenge to drive with one wheel over carpet and said that my wheels are smaller than his wheels. And so he went ahead and made a big stack of carpets and drove his robot over this big stack of carpets. And it really kind of going in a straight line. So I think that challenge, if not simply a straight line, but a straight line with one wheel over a certain percentage of your wheel, like in my case, it would be about half of the radius of the wheel. So I've got to stack some carpets up and run my robot in a straight line over that bump and prove David that I can do it.
I will say, Murray, I think it's wonderful that you've accepted this as a challenge, but I never really intended it as a challenge, but whatever you need for motivation. I was more trying to describe with that little set of videos how a normal PID controller should work and how you would recognize that it was working when it behaves in certain ways.
That was totally the gauntlet being thrown, man, I tell you.
Or the mitten.
The mitten.
On the playground.
Yeah, can I show you guys some show and tell?
Yep.
Yeah, I'll switch my. I thought this on my phone to show some video. 1 second. And, can you guys still hear me? Can you hear me?
Yeah, just barely.
Oh, sorry. Let me Can you guys hear me? Oh,
You're very soft, John.
oh, you can. Okay, cool. Yeah.
Yes.
So,
Yes.
so I mean, I'm gonna show this my screen, but I'll just show you guys. So, what I'm trying to do is to get the odometry going, right? So what I did is, yeah, David last week posted that calibration, so I think it works. What I have is on my PC, I have, yeah, just now we're talking about this architecture with so I have like robot connected with the USB to PC. So I'm talking serial to my robot, which is Arduino. And then on PC, I'm reporting like a logging to bring back the odometry information. Meanwhile, I have this, I just want to test this, like if I rotate, what does it do? If I move forward, so what the behavior? So I'll show you guys, if I do basically this is a counterclockwise rotation. So let's see, counterclockwise rotation. And, oh yeah, it's doing something. And I have some numbers changing. So in a sense, I mean, I'll just show you. So in a sense, I think it's working. I mean, the equation works. All right. Let me. So that's kind of my end of demo.
Making progress. Looking good, but you lost your microphone. Both computer and phone are muted, John.
Right.
There you go. Okay.
Thanks. So yeah, so I think just now you guys were talking about this architecture, right? So yeah, this rings.
Oh.
I just want to tell you guys how I feel on this topic. So I started. I'm more comfortable with computer. So what I'm. Oh, am I turning off video? Oh, okay. Sorry, video on, right? Yeah. Okay. So I started with, okay, I'll program my main logic on my PC, and then just the wheel and encoder go to the Arduino, and it sort of worked. I built from, like, I wrote from scratch. Basically, I have these two sides talking to each other via serial. Right now my trouble is this bulky computer. I have to put my computer on top of the robot. So I think I have to do some rewiring.
Well, John, there are small Raspberry Pi type computers that run Windows.
Yeah.
I mean, they're actually, like i7 Intel chip.
Well, like the Latte Panda, if you don't need an i7, right? Harold is using the Latte Panda.
Yeah. So I mean, there are
Latte Panda. There's somewhere, I would tell you, somewhere between about 150 up to about $300. You should be able to find you a single board computer that runs Windows straight up.
But what about one of those $80 Windows 10 tablets off of
I have a Surface. Even that's kind of big. Yeah. So okay.
John, why can you not?
Yeah, right. Initially, I was trying to put a very small. What was that called? It's like a few-year-old computer, $100. It's too slow. It's too slow.
John, what are you programming your robot in? What language?
Robot is, I mean, on the host is C#.
Oh, okay. Well, that runs on an Arduino.
Yeah, maybe. I don't know. I was gonna really put something on top of the robot and put my laptop on there.
You really want to have a laptop on top of your robot, don't you?
A lot of people do that. If you look at the turtle box and so forth, Almost everybody that runs any kind of ROS robot has got a laptop sitting on top of the robot, or at least did at one time. This is just me personally, but when I pick up my robot and take it out to play with it, take it out around town and let it run around, I don't want to have to carry anything except the robot.
Agree.
I don't want to. I don't want to have a laptop or a Wi-Fi link or anything else. I just want it. That's what autonomous robot means. So why can you not do the processing that you're doing now on the PC? Why can you not do that on the Arduino? Is it not specific for the PC?
So, but my initial thought was, I really want to see what's going on the Arduino. Like, I want to basically, so initially I have the encoder. I try to read the encoder, so I would upload all data to the PC, so I can log it, I can view it, and then when it's good, now I don't have to upload that anymore. So everything. And then it was the feedback. I want to see how the response is on PC and human ID parameter. But now I don't. I'm past that too. So now the feedback is just. Feedback is on the Arduino anyway, but I don't have to do anything with it. Now it's this position control or the odometry. I'm thinking right now what I want to do is read the odometry back to the PC, figure out a path, bring it back to the Arduino, and move slowly, make sure it's working. And then I'm thinking, so like you guys were saying, where does it locate? Whether it's on one side or on the other side, right? So I'm thinking if it's good, if I know it's working, I'll move it to the Arduino side. But before it's working, I don't know. I need to know. I need to see it to know it's working. So that's maybe this is a transition stage that I'm.
John, I have one suggestion that, I won't dissuade you from putting a laptop on top of your robot because it's, obviously that solves certain problems. But I've kind of played around with a number of different alternative designs. And one of the things that comes to mind is there's an Arduino called an Arduino Yun, which is a Rev 2. And that's actually a combination of a really standard Arduino and a little Linux chip on board. And you can SSH onto that board and communicate with the Arduino. So you could effectively have a functional robot running as an Arduino and SSH onto it with Linux and talk to the Arduino from on board. And then if you don't want to use the Linux board, you just don't use it. You just run the Arduino as if it was an Arduino, but you can SSH onto the board. And you could do that.
Wi-Fi type of connection.
Yeah, it's a Wi-Fi connection.
Yeah,
it's either Wi-Fi or a cable, but yeah, it does Wi-Fi.
Yeah, there's a number of those boards out there. I used to have a couple laying around here. Unfortunately, I really liked the Intel Edison, but they discontinued that. That was a really nice board for doing all kinds of things. Murray was right. It was explicitly right in the thing that Murray had. It took Arduino shields. It took all that kind of stuff. Ran Yocto Linux, so you got to do all the fun stuff you got to do. And they just dumped it on the ground.
This is a Nuvoton Tomato board, which turned out to be a lot bigger than I thought it was going to be. But this has actually got a place for an Arduino Shield on it, but it runs Linux. So yeah, there's a lot of these alternatives out there. But basically, the point is that you could have a standard Arduino board of varying power, anywhere from 16 megahertz up to about 300 megahertz, because this runs 300 megahertz. And you've got a full Linux stack on here, so you can SSH onto it. And these aren't even that expensive. And the Yuns are a bit more money. I can't remember how much I paid for this, but this is actually the size of an Arduino rather than something big like this. But having some kind of a hybrid board where you have an SSH ability, you can remote onto your robot, but you're running your robot as a Arduino. And that was kind of the appeal for me, was I would be programming, as David has suggested, I'd be programming my robot in C++, but able to remotely log into it. And that's kind of the appeal for me, is being able to remotely control the robot. And that might be a solution for you.
Gian, I have a question. Does it have to be Windows? Is that one of your main requirements, or it just has to be a powerful computer?
I feel C# is what I'm. I mean, look, if I'm C# is what I'm feeding.
Dude, man, y'all, come on, man. You need to come to my talk, .NET on with a slice of pie on Raspberry Pi. I'm running .NET 5 and all the C# you can handle.
On the pie.
On the pie. Yes.
Nice, yeah.
I'm doing that now. I mean, that what I show.
Oh, that's what you have. Okay.
Yeah.
Is it?
Well,
Is
it's
it?
not exactly what I have now, but I have a talk that does that. I've got a Raspberry Pi sitting right here with .NET 5 on it, and I do a C# into it. I use Visual Studio Code, a remote debug into it from my Windows box. The whole works. You know, it
You see like a remote desktop.
And can you tell I'm excited about it? Can you tell that? Have you got a feeling about that?
So,
you know,
Harold, how do you know what's happening on that PC, on that little box? Are you remoting into it?
With Visual Studio Code, I've got a couple of things that I can do. I can remote debug into that application as it's running right now. I can SSH into it and see what's going on. I don't need a head on it because I've got SSH tunnels going back and forth. And you can even set up an SSH tunnel to like if you got a port that you want to access from your Windows to tunnel it back to your Windows box to see what's coming out of that port.
Mm-hmm.
Yeah. Here, I'll go look a GitHub and you can see a PowerPoint display on it. Hold on a second.
Yeah, my initial thought was, I throw this laptop onto this robot. I have a VNC session so I can, I can see what's happening on that laptop. And being a laptop, it's just it can run anything. But it's a full computer, right? So yeah, but I mean now I think I'm at a point to rewire this to make it compact or like mobile. Right now, look the way I showed you, it can only sit right next to me, and I can't really twist it around for 2 rounds.
John, there's one other thing you can look at. If you can, there are several small radios that can talk to each other. The one that I have the most experience with is the Wixels from TI and Pololu, and it's WIXEL. And you go out to Pololu, and I want to say they're $15 a piece or something, and you need 2 of them. One plugs into the serial port, into the USB port of your laptop, and the other one plugs into your serial port of your robot. And now you can go 30, 40 feet without a wire. All right.
Yeah.
And if you want to, if you're taking this in small steps, okay, this might be the next step for you. I've found them. I use them a lot to do. Is that one? Yeah, that's about the size of them. And yeah, I'm sure Chris would argue for Bluetooth. You can do it with Bluetooth too, I think. Oh, and yeah, that's, what do they call it? XP? Is it XP? Yeah, XP is more expensive, but better. I think, what's the range on that, Dave? XP, what's the range on an XP?
I don't have any real numbers, but my experience is that it works as far as I can see it. Line of sight.
So the Wixel is more limited than that, but it's cheaper than an XP. But if you have two XPs, and I think you need the sockets for the XPs too, because you need a breakout board. It's a little more expensive, but you get what you pay for. But the Wixel is almost dead simple, and I use them a lot for logging, logging information from the computer as it's running. So
they're very easy to use. You just unplug where you did have a serial or USB cable, between the PC and the robot, and you plug one of these in on either end, and that's it.
That's
I
it.
think
Yeah.
by default they come up running a 9600 baud, but you can go in and program that. And interestingly enough, it uses old modem, Hayes modem control sequences, you know, the AT sequences. But you can reset the baud rate. I believe I run the one I just held up. I'm running that one at 19.2. But I think that their upper limit is 38K, if I remember right.
Wixel, I run my Wixels at, was it 56,700? That's, or 52,600, I can't remember. It's 5,000 something, 50 something, 50,000 something. And I run them.
I think that's the way I'm gonna go. I think it's gonna, yeah.
If you need help with the Wixel, if you need help with Wixel, you can email me and we can talk about it, because it's,
yeah.
but like I said, they're not, I like, the XBs are very good, okay? Not taking anything away from them. But if cost and simplicity or you're driving and you don't want to go line of sight, then I would say a Wixel might be a bit. That's just, and like I say, you can get them from Pololoo, and they have good documentation, and they come with essentially about 10 canned routines, and you just pick which of the canned routines that you want. So like if you're gonna, one might be serial to radio, well that's the one you would put on your robot, and the other canned routine might be USB to radio, and that's the one you would put on your PC.
Yeah. So John, the link I put in the meeting notes is I did an hour talk about, I don't know, a couple weeks ago or so.
Yeah.
On that Raspberry with Pi, and that's the recording of that talk.
Yeah.
You got any questions? All you gotta do is ask, man. I'm good with that.
Cool. Yeah. Thanks, Harold.
You know, Microsoft MVP and all, it's my job to help folks become more Microsoft if they wish to be.
C# guys. Thanks, Harold.
C# person and C# all on there, man.
Nice. One last thing I want to ask you guys. So when I did my odometry, I'm trying to share my screen here. So initially I named my wheel. So if you see my arrow here, do you guys see my screen?
Yep.
So initially I put it as let me see. Oh yeah, so this is my wheel sequence. Like 0, this is my 4 wheels, right? 0, 1, 2, 3. I mean, I just thought, okay, that's how I would index it. But then when I'm using the odometry calculation, it's some paper, but yeah, they name it like 0, 1, 2, 3. I'm thinking I can change my convention, but is there a convention for indexing the wheels? Do you guys know? Yeah, Carl? Oh yeah, sorry.
Carl, you muted.
I was saying good night to Chris. Sorry. No, but what does it really matter, Sean? What you call the wheels?
It doesn't really matter in my code.
Fred and
I would
Nancy.
match it. but I was just wondering, is there a convention at all, or is this?
I mean, in mine, I have left front, left rear, front right, front rear. Just pick one and stick with it, right?
Yeah, and I went port and starboard because I have, I used to go sailing.
Okay.
Carl, you don't really have one that's called front rear, do you?
It's a multi-dimensional robot. What can I say?
Okay, I see. So there's no real convention. All right, I'm fine. I have my convention. Cool. All right, so that's my update. I'll try that radio connection. Thanks, guys. I'll see.
Actually, I wanted to ask Doug about the difference between the XBs and the Wixels. I was just looking at both on the website, and the SparkFun website has what looks like a half dozen, maybe even a dozen different XB boards of different types. And then the Polar one only has a few Wixels. And I take it that the Wixels only can be connected by USB. So you have to use USB, or can you connect to
it can be serial or USB.
Oh, okay.
I think that's what I've used it for. Like I said, they have about 10 canned routines, and you basically pick the routine that you want to use. So you don't you program it, but you don't really program it. You know what I mean? You just select a program basically, and it does that one function. And like I say, the two I have are USB to radio and radio to serial. And I mean, I really never had to use them for anything else. That's, you know, and in my case, I actually won them in one of our contests, so I didn't even pay for them. So, but I use them a lot for when I use them a lot when a robot gets to a certain stage of development, you know, and then they're on there all the time. And I have nothing wrong with XB. I mean, I think XB has a longer range, but I believe in general on radios, the longer the range, the slower the less bandwidth that you're using. And so usually you can't quite go up in baud as far, but David said he went up to what, 19.2. So, I mean,
yeah, that's. But really, I was running that because that was the default of the microcontroller I was attaching to. Donna, I see you trying to say something, but you're muted.
Oh, no, I actually, yeah, I was, yes, I did, I have my hand raised, but I just want to get in the queue for Q&A. That's all. That's all I raised my hand for.
Well, go ahead.
Oh, okay, thanks. So first off, I don't really have any demo or specific project information to share today, but I wanted to ask some questions on some technology and a new learning area that I want to pursue. So I'm real interested in learning about SLAM for the idea about, you know, well, either indoor or outdoor navigation, path planning, that kind of thing.
Mm-hmm.
And I know that everything so far that I've read about SLAM sounds like, as far as one of the primary sensors that you have to use for that technology is a LiDAR sensor of some type or another.
That's one way of doing it.
Yeah, right. And so I'm assuming, you know, kind of reading between the lines and extrapolating for my own circumstances, since I don't believe really have any LiDAR sensors myself. That's a follow-on question that I have too about LiDAR, but I'm just wondering about what other, if anybody here in the group has SLAM related experience, and also the dependency or not of LiDAR with SLAM. So that's kind of my first question.
What do you mean by dependency?
Oh, well, in other words, if the algorithms, if the architecture itself, as far as you know, calibration, and I'm sorry, not calibration, as far as fusion of data, and you know, the types of algorithms that SLAM is utilizing, if LiDAR is required or a dependency. That's what it is I mean by that.
I think, you know, it depends on where you want to go with it. If you're talking about something like a NITO, you know what a NITO is, right?
No, I don't.
Okay. It's it's like a Roomba.
Oh,
it's
okay.
like a Roomba, but it uses SLAM. And one of the things that it can do is, like in a Roomba, it goes all over your floor. It just random walks all over your floor.
Mm-hmm.
So on a NITO is going to go back and forth, back and forth, back and forth. Okay, and it's going, and when it gets finished with your room and it finds a door, it's going to go into the next room and do it and keep doing it. And then its battery's going to go down and it's going to find its way back and go into the charging station. And then once the charging station is charged, it'll go back to where it left off and continue to do that room and then follow off into the next room and so on until you block it off. So, I mean, it's very sophisticated for $400 thingy. And it has a LiDAR on it, which you can buy on eBay or where. I wouldn't do this. I've got them, but I wouldn't suggest it. You can buy them for about anywhere from $60 to $100, depending on availability. But
I'm not certain. I could be wrong on this, but I don't believe anybody in our group has ever implemented
something that sophisticated. Right.
So,
now,
but I can take that as close as I've come to that. I've been able to do pretty good mapping using my sonar. So I don't think that. I think that what you'll find if you go look online is that everybody who has written the SLAM package has assumed that you would have a LiDAR.
Right, that's what it is. I've seen. Yeah.
Yeah, but it's not necessary. It's just that there are some real disadvantages to a LiDAR that we've talked about before, in particular because, it's a laser beam and it has a very small dwell. So really you're just getting a slice of the environment. So for example, if you have something that's got, a foot sticking out at the bottom of a leg, it'll see the leg but not the foot. So there are some disadvantages. Most of the ones that I've seen functional usually operate in pretty simple environments. And so that's the way they solve that problem. I'm not certain how valuable SLAM would be outdoors, because the idea is that you're going to have a map and you're going to use that map to do navigation. Outdoors is pretty big. My own experience is that I have found what I believe are better ways to navigate without requiring a complex map like that. The second observation I would make is that you have to deal with the fact that the map changes and that your position on the map changes. So, for example, house people move chairs all the time.
Hey, developers, smartphone.
They have a map that cleverly goes around the chair where it was at that time you look, but it's not there now. In those cases, in terms of, when we talked about this before, someone who had more experience, it might have been Chris, suggested that even if you do have LiDAR, you still need a full suite of other sensors for obstacle avoidance and so forth.
Okay.
Yeah, you can do it with cameras, the Intel RealSense, like either the D415 or the 435. And I think, I want to say they use a T265 camera with that. And that can do, there's, I guess it's, they developed algorithms to be able to do SLAM, and in fact, part of their demonstration is that, they show it, how to do SLAM with that. But a long time ago, Jason had a TurtleBot, and he was using what was an Xbox 360 sensor on the TurtleBot to do SLAM.
Right. Now I'm just sending out a link from an Instructable on adaptive mapping.
Oh, okay.
And he's using an iCreate robot base. Don't worry about that. But when it all boils down, what he's using is a sharp IR sensor, just like David was talking about with sonar. And this is kind of like, SLAM can get really, really, really complicated. But this kind of can show you a simple version of mapping, okay, on how to do it. There's also, I'd have to think about it, but there's also some route planning type stuff that can go with this that can use this information and plan your route better. I'll have to think about where a good link for that. But this one will get you, it's very simple. And there may be another Instructable that's by the same author you might want to check. the author's instructables and see. But this one, like I say, it's just essentially one of the questions that you always have with SLAM and is, okay, if something steps into the picture, okay, it wasn't there before, but all of a sudden it's there, you know, do you remap it? And we actually had access to an Edo engineer talking about their system one time, and he said that they do it if they see it twice.
They do what if they see it twice? You mean they do avoidance? You mean?
No, if something steps into the path, like let's say you walk into the room and your robot's running around, but you weren't in the room a minute ago. Well, when the guy's scanning, making his little scans, okay, and you'll see why LiDAR is cool, because it can go around and get you all of this in one big cell swoop. Where this little IR guy, what he's doing, he's going to be looking this way, and then he's going to look this way, and then he's going to look this way, then he's going to look this way, and then as far as he can see, you know, he knows where he's clear, okay. So if you tell him to go across the room, and he looks that way and he sees there's nothing ahead, he goes ahead. You know what I'm saying? And then when he gets to a point there, then he's going to do the mapping, because all he has is essentially a single bit sensor. You know, he's got that. Where on the LiDAR, you know, he's whirling around. He's getting a whole picture of the room all the time. But it's the same.
Plane in the room, yeah.
Yeah, so it's the same concept, though, of knowing how far things are in the given directions. You go ahead and just look at it, and I think you'll find it interesting.
Okay, yeah, okay, good. It kind of sounds to me like behavioral robotics is, you know, as far as a more adaptive, on the fly, non really path planning type of, and especially in an outdoor environment, is a better alternative to SLAM.
Donna, there was about 20 years ago, I published a little paper about how to fold navigation and odometry into a standard subsumption stack.
Oh, right.
And,
okay. Right.
And I first published that in the Seattle Robotics list.
Oh, okay.
Yeah,
okay.
some many years, and there were long conversations about that. It occurs to me now that that's still not widely known, and that it might be useful for me. Carl asked if we would give a talk sometime later this spring, and it might be useful for me to give a talk on how you do that, how to do navigation without a map.
Okay, yeah. Okay, so you're David Anderson then?
Yeah.
Yes, ma'am.
Oh, okay. I've been seeing you all these weeks, and I didn't know that you were David Anderson. I know I've read I've seen a lot of your code and a lot of your articles. So very good content. Very good content. Okay.
And you're Donna Seattle.
Yeah. Well, I'm Donna Smith. I'm from Seattle. So.
I'm David Denton.
Okay. Okay.
That's Murray, New Zealand up there.
Yeah.
Okay. Okay. Yeah. All right. And then the two more points I wanted to make regarding SLAM and LiDAR. So especially David, you're probably best to answer this, but do you know of any controller, appropriate as far as power and that as far as a great controller that would be recommended to run SLAM if I decided to go in that direction? What would be a good microcontroller? Or
there was a guy who was vice president of our club for a while who formed a company called Surreal, and I believe he makes a little controller exactly for that LiDAR. Has anybody here used his controller?
I've used it.
Now that you know of which I speak, you might look at that Surreal. It basically just has the PID controller and does the data conversion. Now that's just for the device itself. That's not
for doing the actual slam shot
Yeah.
to read the device.
And
I don't know what you're comfortable with. What language do you want to write in? What kind of hardware are you comfortable with?
Oh, I'm sorry, David. Was that a question to me?
Yes.
Okay. Okay. Well, yeah. I'm trying to learn the scope of what at this point, more of what SLAM is all about, and basic sensor requirements. That's why I'm kind of starting with the questions that I have tonight. But ultimately, I would love to incorporate that, especially for an indoor navigation type robot, whether it just be an intelligent bot to run around the house, whatever. Or for a specific indoor type navigation contest. Either one.
You're not talking about the beer from the refrigerator, are you?
Asking a question about favored controllers is like bringing up, religion or politics.
Yeah, well, I wasn't necessarily asking for favorite controllers. I was thinking about a controller that can run SLAM is basically what I was trying to ask. But
I think in this group, there's some people who have the Raspberry Pi type Linux environments, and if you're comfortable in that kind of environment, that's very powerful. And then most of us use single board computers. I like the ones from STM, but they're also fans of the ESP32 here, which has some very cool things about it, like built-in Wi-Fi and stuff like that. But again, that depends on what kind of environment you're comfortable in. I write everything in C. And so
me too.
I have, okay. So if you have the GCC tool chain as your development environment, it has a whole bunch of cross compilers.
Right.
And so I have a cross compiler for the ARM chip. I use the no architecture tool chain for that. And I compile everything on my Linux machine and then download it. The STM boards have a little sort of co-processor that can program the board, the debugger. It's very cool. And so you just hook up to it and basically drag the file and it programs it. It's very, very easy to use. But again, that's my own particular preference, and that's what I'm comfortable with.
Yeah, right, exactly. Yeah.
Donna, another one that you might want to look at is the Teensy boards.
Oh, okay.
They're I want to say that they're compatible with Arduino, so they're easier to use, but they're powerful because they're an ARM chip.
Okay.
I'll put Teensy as well for those very reasons. You got a high clock rate on them and lots of memory and lots of pins.
So I'm just saying that's an alternative.
The other one, Doug and Donna, is that the ESP32's become very popular with a couple different companies, and Adafruit has just released, I think within the last month, what they're calling a Feather S2, which is $22, and it has a 240 megahertz 32-bit ESP32 on it with Wi-Fi. And it's a tiny little board. They're pretty cool, as David was saying. I mean, these are beautiful little boards, and if you're comfortable programming where you've got Wi-Fi and a 240 megahertz processor for $22, and it's about that big, it's pretty good.
Yeah. What was the name of that board again?
If you go on the Adafruit website and search for Feather S2, just as one word, Feather S2. Their Feather boards are a whole series, and this is a Feather that has an ESP32 on it.
Oh,
okay. Does it have an S2, ESP32S?
Week or so, Raspberry Pi has put out something called an RP2040, which is their entry into the microcontroller space to compete directly with the ESP32s and all that sort of things. They have a reference board that's $4. If you want to get that, if you want to get out some bells and whistles from Adafruit has, I think they're like $20-25 for their board that has all the bells and whistles on top of the reference board. That codes like an Arduino, but it has a lot more juice to it. I don't have the specs handy, but if you look up an RP2040, that's their name. That's their
Harold, did you watch the video link that
that Carl posted about that?
No, I didn't.
Okay, well, you should.
Okay.
Yeah, there we had a mailing list discussion about that. I had posted about the RP 2040. My take on it, I've actually got one coming in the mail. My take on it was that I wanted to see if, as Donna was saying earlier, that I want to see if it's possible to use it as a sub-processor off of a Pi, and apparently it is, but maybe no more than a Feather S2 or anything else. That the one thing about the RP 2040 that's a downside is that it's actually a Cortex M0, so it's kind of the low end of the Cortexes right now. No M0.
2 M0s. 2 core.
Oh, two core.
Yeah.
And that's pretty fast. Yeah. It's like, I think up to 200 megahertz. One thing I was going to ask Donna is that I kind of looked at SLAM as a possible interest like a year or so ago. And rather than go full SLAM, I ended up mounting one of, if I can find it, one of these little guys, the VL53L1X, which is a single leader that doesn't spin in place. I can't see myself on the camera, but basically it's a little tiny lidar that I have mounted on a servo, and I just do a little slow sweep back and forth. It's got a range up to about 3 meters. The alternative would be either, let's say, as David said, an ultrasonic. If you don't want to go full spinning lidar, you could go with an ultrasonic on a servo. There's also this, which is a sharp infrared, analog infrared, runs up to 5 meters. This is a big, powerful, the biggest one they make, up to 5 meters. I'm using analog ones up to 1.5 meter on the front of 5 of them on the front of my robot. So you could go with a little servo-mounted lidar. You could go with big or small infrareds or ultrasonic, and kind of not go the full SLAM route with a spinning, complicated lidar as an alternative to make things a bit simpler. But I mean, certainly if you're going to go, what's that?
To
To start off. Yeah.
Okay. Okay. Yeah, that's interesting.
Because I will tell you this: if you're using a spinning lidar, and even if it's the inexpensive ones are, I want to say they're 30 RPM, so that's one cycle every half second, I guess. And is that right? No, it's 30 per second. 30 per second. Anyway, I mean, they put out a buttload of data. I mean, absolute buttload of data. And keeping it up with it is really tough. It's not an Arduino, not an Arduino. The Teensy can handle it, but you don't want to be doing it with an Arduino Uno type board. Okay.
Yeah, that ESP32 could probably handle it at 240.
Oh, yeah. But the problem with that is a lot of times you don't want to screw with Wi-Fi, which is also a big hog on power. I mean, I really not that interested in having Wi-Fi on my robots. There are projects that I'd like to have Wi-Fi on, but not my robots. You know.
Yeah, the other, the last point or question I was going to make is, like a lot of us here tonight, we get freebies, you know, as far as sensors and stuff that we've won at contests or whatever. And I have one that I've had for, I think it's like a couple of years, and it's an old parallax part. I'll put the URL in the chat. Okay, just a second here.
I'm afraid I have to go. We got dinner here at this side of the world. So we'll see you guys. Actually, I'm not going to be able to make it next week. I've got a business meeting I got called into, but so have a good week though.
See you.
See you guys.
Have a good week, Maury.
We'll see you.
Let's see. Did I post it? Let's see. It will be.
Yep, you got it.
Oh, okay. All right. Okay. So, okay. Anyway, sorry, I posted it twice. The same link, but anyway, it's I'm just wondering with this part. It's listed, of course, as a laser rangefinder, and from what I can tell, is in looking at the specs and all, is that this is very much like a LiDAR. I mean, you know, of course, it's going to be older technology. It probably doesn't have the resolution and all that. But I'm just wondering about what you guys think about if it's, you know, if it really qualifies as a LiDAR. It's kind of a nervous read that I see, that you have to be very careful, you know, about the not looking at the laser at all. It's you know.
Don, are you familiar with the sharp infrared distance detectors?
Yes, I am. Yeah.
Well, that's really very much the same thing. They're using parallax, basically. On the sharp detectors, the way it works is there's an infrared LED laser, and there's a linear element behind the lens. And so since the two of those are off angle from each other, the closer you get, the further it moves across the linear element. And that's how it does distance. And so I believe that's the same thing. That I don't think that laser rangefinder is measuring speed of light. I don't think it's time of flight. I think it's parallax. And you know, in terms of its range, you can buy those sharp IR detectors with about the same range. They're pretty easy to use. You just hook them up to an A to D port. You have to do a little bit of conversion to turn their input into an actual distance, and they're fairly cheap, and they're infrared, so you don't have to worry about blinding your kittens or anything.
Yeah, right. Right. Okay. So in other words, LiDAR is based on time of flight sensing.
Well, not always. No, not always. Not always. So a lot of the spinning ones are not time of flight.
Okay.
Okay, they're the same thing that you got, except they're spinning.
Oh, okay. Well, okay, but this one, of course, I could mount it on a turret, you know, and spin it.
Well, I was looking at that price. There's so many probably nicer options today.
Yeah,
I'd never buy that part for $99.
Oh, well, no, I mean, I just I got it free.
Free, I know what you mean. So I mean, that's worth messing. I mean, it's hard to beat free. So you know, it's worth messing with you. But there might be some things that are a little easier to use. If you want an I2C sensor or a UART sensor, a serial sensor, there are little Chinese ones that are $20. What are they called, Ray? You know, they're little tiny ones. I've had one I can show you one.
Oh, like the V, I forget what it starts with a V and
No, I wouldn't go there. I find those hard to use and a little weird. I'm thinking about something like a teeny micro or micro teeny. Let me. You guys, I'll see if I can find one and I'll show it to you.
Well, good, because I want to jump in here with a pet peeve. That is to say, all this hardware over the last 30 years has gotten so cheap. It really has. That shouldn't be a part of your decision making. You're going to decide whether to buy a part for $20 or $30 and then spend 1,000 hours programming it. There's where the money goes, not the part. Also, I must say, replying to something Harold said earlier about the Discovery Board, that I've learned is that once you settle in on a board, you need to buy 5 or 6 of them, because when that one dies, that company won't make it anymore. As a matter of fact, they'll have gone out of business. You know, you got to buy multiples of everything.
And that's what happened to his Intel Edison, right? That killed Omar in his Orbi ball.
Okay, anyway, that's all I had for tonight. Thanks for the advice and
Doug, were you thinking of a LiDAR light?
Oh, well, I was just thinking about LiDAR sensors, current LiDAR sensors that developers or roboticists are using to implement SLAM. That's what it is I was asking about with LiDAR. So
Doug,
I'm just
Doug, were you thinking of the LiDAR light? Was that what you were trying to recall?
Donna, do you monitor the Homebrew Robotics or the Portland, Seattle
Oh, I used to, but I haven't for a while. I am on their mailing list. I am on their
I
mailing
think
list.
they have some SLAM expertise in those groups.
Oh, okay.
So you
Okay.
might ask.
Okay. All right.
Yeah, I would say actually doing like a SLAM algorithm, if you're using like a rotating LiDAR, that's going to take some performance. I don't know that you could do it with even an ESP32. I don't know if it'd have enough horsepower. You know, they used to do it in ROS with, you know, you had like an i5 or an i7 laptop, you know, that was actually implementing the algorithm. So it's you might be able to do it with like a LiDAR and you know, on a servo, because that's much slower. But you know, rotating one, you're getting 360 readings every 200 milliseconds. You know, it's kind of spitting right out of the thing. So, Doug, can you hear me?
Yes.
Okay. Were you thinking of LiDAR Lite? Was that what you meant?
No. I was trying to get a introductory, inexpensive one, and I think I found it. It's Bennyweight sensors.
Benawaki.
Yeah, or
That's
is
what
that it? Benawaki?
I don't know.
Yeah. Anyway, this is their cheapest one. It's about $20.
Is it that cheap? It used to be like $40.
No, that was what was confusing me, because it was the one that's $40 is this one, and it's called a TF Mini Micro, and it's about $40. But this one is only an 8 meter LiDAR, and it's $20.
Yeah.
And I didn't have enough time to look up and see if it's whether it's I2C or I don't know what the interface is.
Yeah.
Yeah.
Yeah. And that one may not even be laser. It may be LED.
Yeah, it might be.
Yeah.
But 8 meters for indoors is fine. I wouldn't worry too much about it. But I'm trying to figure out where it's UART/I2C. So it sounds like it's a 3.3 volt TTL levels. So I would say that just looking at it, it's probably either I2C or serial, depending. There's probably a switch or a pin or something that you have to, or a jumper that you have to set. But anyway, that's the most inexpensive one I know. That's probably the least amount of pain. Okay. And it's not much different from the one that Dave was talking about, but in this case, it actually uses time of flight, and it's a little more modern than the Sharp sensors. And it's not quite so. A lot of the Sharp sensors have this distance that you have to be beyond before it'll accurately measure. So you might want to, I don't know, this one, you might want to, like I say, if you want to have a 20 and you want to slap it on something, it's right up, that's Robot Shop, right up there in Canada near you guys. So.
And it has a little smile on the front of it.
Yeah.
Yeah.
Gentlemen, I'm done.
I'm done too. Yeah.
It's getting late.
Well, I want to pop in with a quick question and then maybe an observation. The quick question has to do with our API. Are we APIing just a telepresence robot or a general autonomous robot?
I would propose a general autonomous robot, but
that's what I thought.
That's just my preference.
Just wanted to make sure.
And we haven't, I know we haven't had a chat on that. This Iron Rain, I think, helped and other topics, but maybe next Tuesday we should force ourselves to spend some time on that, Doug.
Yeah,
agree.
And I know John's nodding his head too. And
Yeah, Tom,
there's one other thing, and if nobody people wouldn't mind, I think maybe we could do it in this meeting as well, Tuesday, versus having a separate one. But we could do that if we wanted.
right. I'd propose doing it first thing and then do the updates.
First. Oh yeah, yeah. Okay, good. Let's do that next Tuesday. And then the other thing that I was hoping to do next Tuesday or this Tuesday and we didn't was on our monthly meeting on the 13th, so a week from coming Saturday. We have graciously got Kareem and Dave and maybe Jesse Brockman from Colorado and Scott Gibson to serve as panelists for an outdoor rover expert discussion. So I was hoping that in this Tuesday session next time, we could take some time and just queue up questions from the group and then just have an open discussion on what are the questions, not answer them Tuesday night, but just ask what are the questions people want to know. And then I can start to compile them and then we can start that to seed the discussion next Saturday.
Okay. Well, along those same lines, I have a thought I'd like to plant in your brain. It doesn't require a response. I personally have found these online RBNOs much, 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 much more valuable than I ever found the in-person ones. They're more organized. Everybody has everyone's attention at some time. And we get people who are not from Dallas. Mm-hmm. And so the idea that we're going to go back to doing it the way we used to is not something that I'm looking forward to.
We either need to do both or combined, which I think is part of the purpose of the telepresence.
But I think it's what we were talking about anyhow,
right.
But it feels to me like that's far enough away anyhow that August. So, but thank you, David. I mean, it does. I mean, I think a lot of people would agree that, hey, you voting by feet, right? Look at how many people here. We've been on for 3.5 hours and we still have 9 people online.
Yeah, I haul ass home through the crap so I can try to get home in time.
Yeah.
But I have found these extremely valuable.
Yeah.
I gotta agree. I would be here if it weren't for that.
Well, then,
on the other hand, it's 11 o'clock now, so we do need to hang off. I mean,
and it's midnight here in Pittsburgh, so good night, Joe.
One quick observation related to what Donna was saying is that I think that whole discussion was about 2 different conflicting or parallel types of things. There's object avoidance, and then there's mapping, which gives you navigation planning. And I don't think they're mutually exclusive. So just my observation. That being said, I'm out of here.
Oh, that was a deep opener, but bring that up this Tuesday night. Good night, Joe.
And thanks, guys, for all the feedback tonight. It was enjoyable discussion.
Yeah, thanks. Quick question. I buy 2 of these Wixel